Subscribe to the channel and like the video. Somewhere in the quiet depths of space, far beyond the reach of our eyes and yet so close to the yearning of human curiosity, a cosmic miracle unfolded. Imagine a corpse stirring from its eternal rest, a being long declared dead suddenly gasping back into life. That is precisely what happened in 1996, when astronomers around the world were stunned by the sudden reappearance of a star that should not have existed. This was no ordinary star. It was Sakurai's object, a stellar ghost in the constellation Sagittarius, a star that had already died, transformed into a white dwarf, and then, against all cosmic odds, seemed to resurrect itself in a blaze of brilliance. For the scientific community, it was as though the heavens themselves had rewritten the script of stellar evolution, as if the universe wanted to remind us that even in death, stars might hold one last secret. This astonishing rebirth shook astronomers to their core. Stars are supposed to follow a predictable, almost mechanical journey from birth to death. They do not come back to life. Yet here was a star that defied the rules, a phenomenon so bizarre that scientists called it a born-again event. To the untrained eye, Sakurai's object appeared to be a new star blazing into existence. But to those who understood stellar life cycles, it was infinitely stranger. It was the ultimate cosmic twist, a star that had died billions of years ago, suddenly reversing time, swelling again into the stage of its youth. Like an elderly person turning back into a child overnight, it was a vision that seemed both impossible and profoundly real. This is not just another story of astronomy, it is a story of resurrection, of witnessing the impossible, of seeing the universe break its own rules. When Yukio Sakurai, an amateur astronomer in Japan, first noticed this sudden outburst of light in 1996, he thought he had discovered a nova, a new star. But in truth, he had stumbled upon one of the rarest and most precious events ever recorded in astronomy. From that moment, telescopes across the globe and even the legendary Hubble Space Telescope turned their gaze upon this celestial enigma, desperately trying to capture every flicker, every pulse, every whisper of this star's strange journey back to life. For astronomers, Sakurai's object was not just another point of light in the sky. It was a time machine. It allowed them to watch stellar processes that usually take thousands, sometimes millions, of years unfold in mere months. It was as if the star had pressed fast forward on its evolution, racing through phases that could usually only be studied in theory. And so, in the heart of Sagittarius, about 20,000 light-years away, this zombie star became one of the most important laboratories in the cosmos. To tell the story of Sakurai's object is to tell the story of life, death, and rebirth written in the language of the stars. It is to understand how stars like our own sun will one day meet their end, and to marvel at the rare exceptions when nature throws the rulebook aside. It is a reminder that even in the vast emptiness of space, where time seems endless and unchanging, miracles can still happen. Miracles that remind us how fragile, how unpredictable, and how beautiful the universe truly is. To set the scene of this remarkable tale, we must first travel, at least in our imagination, into the vast wilderness of the cosmos, to a region of the sky that has fascinated astronomers for thousands of years. The story of Sakurai's object begins in the constellation Sagittarius, a place that lies in one of the most majestic neighborhoods of our galaxy. If you were to look at the night sky on a clear evening, especially from the southern hemisphere or near the equator, Sagittarius would reveal itself as a cluster of stars that many say resemble the outline of a teapot. But this whimsical teapot shape hides something far more profound. Sagittarius points directly toward the very center of our Milky Way galaxy. When you gaze into this constellation, you are looking into the heart of our galactic home, a region filled with countless stars, swirling nebulae, and mysteries still untold. It is here, about 20,000 light-years away from Earth, that Sakurai's object quietly resides. 20,000 light-years. It's a distance so vast that it's almost incomprehensible. To put it in perspective, a single light-year, the distance light travels in 1 year, is about 9.46 trillion kilometers. Multiply that by 20,000, and you begin to grasp the immensity. The light that we see from Sakurai's object today began its journey back when early humans were painting on cave walls, long before the first civilizations had formed. By the time its rebirth in 1996 reached our telescopes, humanity had already invented cities, telescopes, and space exploration. In a very real sense, when we look at Sakurai's object, we are not just looking across space, we are looking deep into the past, peering at an ancient event only now arriving at our eyes. The star is located in a dense region of the Milky Way, toward the bulging central core of our galaxy. This area is rich with interstellar clouds, clusters of stars, and glowing remnants of other stellar deaths. It's a place where stars are born, live, and die in great numbers, a cosmic laboratory filled with beauty and destruction. The interstellar medium there is thick with gas and dust, making it a challenging area for optical observations. Often, astronomers must rely on infrared and radio telescopes to pierce through the murky veils of dust that obscure our view. And yet, despite being hidden in this crowded galactic heartland, Sakurai's object managed to reveal itself in spectacular fashion. One of the most striking aspects of its location is its association with a planetary nebula. Long before its dramatic rebirth in 1996, Sakurai's object had already gone through the process of stellar death typical of stars like our Sun. When a Sun-like star exhausts its nuclear fuel, it sheds its outer layers into space, forming a glowing bubble of gas and dust known as a planetary nebula. These nebulae are often breathtakingly beautiful, shining in vivid colors as ultraviolet radiation from the hot core ionizes the ejected gas. And indeed, surrounding Sakurai's object is just such a nebula, the silent evidence of the star's earlier demise. Astronomers had catalogued it before, not knowing that within its center, hidden within the ashes of its first death, a resurrection was quietly waiting to happen. This makes the constellation Sagittarius an even more fitting backdrop for our story. For Sagittarius is not only home to the supermassive black hole at the galaxy's core, but also to countless relics of stellar birth and death. Nebulae such as the Lagoon Nebula, M8, and the Trifid Nebula, M20, are there, regions where stars are born. The globular clusters M22 and M28, ancient stellar populations, also reside in this part of the sky. And tucked into this busy galactic scene was Sakurai's object, its light dimmed by intervening dust until that fateful February of 1996, when it burst into brilliance. Another layer of wonder comes from the fact that, though 20,000 light-years may sound impossibly distant, it is close by galactic standards. Our Milky Way is about 100,000 light-years across, which means that Sakurai's object lies within the inner third of our galaxy. This proximity, cosmically speaking, allowed astronomers to study its evolution in unprecedented detail. If it had been twice or three times as far away, the light would have been fainter, the details harder to observe. But at its distance, the star's sudden brightening made it just visible enough for amateurs like Yukio Sakurai to catch sight of it, even with modest equipment. That accessibility was one of the great strokes of fortune in this entire saga, a cosmic event of staggering rarity happening in a place close enough for us to witness. Consider, too, the poetic symbolism of Sagittarius itself. In mythology, Sagittarius is often represented as a centaur archer, bow drawn, arrow aimed at the heart of the scorpion, the constellation Scorpius. To many cultures, this figure symbolized a bridge between the human and the divine, the earthly and the celestial. And in a way, Sakurai's object embodies that same symbolism. It became a bridge between life and death, between the expected order of stellar evolution and the chaotic surprises that the cosmos still holds. Just as the archer points toward the galactic center, the symbolic heart of our galaxy, Sakurai's object points us toward a deeper understanding of the life cycles of stars. When astronomers realized the location of Sakurai's object, they knew immediately that this wasn't just a random flare or nova. Its placement within Sagittarius and within a known planetary nebula meant they were dealing with something far more complex. They weren't watching the birth of a new star, but rather the astonishing return of one that had already died. The fact that it happened in such a rich and significant region of the sky gave the event an even greater sense of drama, almost as though the universe had chosen the stage most fitting for such a grand spectacle. And so, as we set the scene, we imagine the constellation Sagittarius stretched across the summer sky, its teapot-shaped stars glowing faintly against the cosmic background. Within its borders, hidden among countless other lights, lies the faint and shrouded Sakurai's object, a star 20,000 light-years away that, in 1996, broke its silence and flared back to life. It is here, in this galactic heartland, that one of the rarest events in astronomy unfolded, a resurrection so unlikely that only a handful of such occurrences have ever been witnessed by humankind. The discovery of Sakurai's object is a story that blends chance, passion, and the enduring truth that sometimes the most groundbreaking moments in science are not uncovered by vast research institutions or massive telescopes, but by the sharp eye of a dedicated individual. The year was 1996, a time when astronomy was already undergoing a quiet revolution with the arrival of more powerful telescopes, space-based observatories, and increasingly sophisticated computers. Yet, in February of that year, it was not NASA, not the European Southern Observatory, nor any of the great astronomical hubs of the world that spotted the mystery of Sakurai's object. It was a quiet man in Japan, Yukio Sakurai, an amateur astronomer who, with modest tools and an unwavering passion for the stars, found something that would stun the global scientific community. On the evening of February 20, 1996, Sakurai was conducting his regular observations. Like so many amateur astronomers around the globe, he was not armed with the enormous observatories of the professionals, but with patience, discipline, and a trained eye. He scanned the constellation Sagittarius, a region already crowded with stars and nebulous clouds, when he noticed something unusual, a new point of light, a star that hadn't been there before. To his astonishment, this star wasn't on his charts, and no record of it existed in prior catalogues. It shone brightly enough to be seen with small telescopes, an unmistakable interloper in the sky. At first, Sakurai thought he had stumbled upon a nova, a well-known type of stellar outburst where a white dwarf in a binary system suddenly brightens after accreting material from its companion. Novae are not uncommon, and when a new star appears in the sky, this is often the cause. Indeed, throughout history, many sudden stars that appeared to observers were novae or supernovae. But there was something different here. This star didn't quite behave like an ordinary nova. Its spectrum, its brightness, and its peculiar placement inside a planetary nebula made astronomers scratch their heads. Sakurai, like all good observers, did not dismiss what he saw. He recorded his discovery and reported it to the Variable Star Observers League of Japan, VSOSOS, a network of astronomy enthusiasts and professionals who share findings of unusual stellar activity. His report quickly spread. Astronomers across the globe turned their telescopes toward the coordinates he provided, eager to verify and understand this sudden intruder. What they found was beyond their expectations. This new star had been catalogued before, but only as the faint, nearly invisible core of a planetary nebula, evidence of a star long dead. For decades, it had slumbered in obscurity, the white dwarf remnant of a star that had already shed its outer layers. It was not supposed to return to brilliance, not supposed to suddenly flare up again. And yet, here it was, shining with the unmistakable brightness of a star that seemed reborn. The astronomical community was electrified. Here was not just a nova, but something almost unheard of, a born-again star. The resurrection of a white dwarf through a rare process known as a very late thermal pulse. What Sakurai had stumbled upon was an event so rare that only two other possible cases had ever been recorded before: V605 Aquila in 1919 and FG Sagittarius in the 20th century. But Sakurai's discovery was unfolding in real time, at a pace so rapid that changes in the star's light and atmosphere could be tracked week by week. It was as if nature had handed astronomers a live experiment, a chance to watch a star defy death before their very eyes. The immediacy of the discovery gave it a kind of drama seldom seen in astronomy. Often, the events we observe in the sky are so far away and take place over such immense timescales that we only catch fragments, shadows, or echoes. But with Sakurai's object, evolution was happening so quickly that scientists could watch entire phases of stellar transformation within a single human lifetime, sometimes within a single year. In 1996, right after its discovery, the star brightened dramatically. For astronomers used to watching stellar evolution over geological timescales, this was like a tree sprouting, blooming, and withering in the span of a single afternoon. The discovery also underscored a powerful truth about astronomy: amateurs still play a vital role. Despite the vastness of modern observatories, it was the dedication of an individual with a modest telescope that brought this phenomenon to light. Yukio Sakurai joined a long tradition of amateurs who had made groundbreaking contributions, from the discovery of comets to variable stars, reminding the world that the night sky is open to anyone with the patience to look. Within weeks, professional astronomers rushed to study the object with the best instruments available. The Hubble Space Telescope was directed toward it. Infrared observatories joined the chase as the star's light began to dim behind thick clouds of dust it produced. Ground-based observatories across Japan, Europe, and the Americas poured resources into documenting every flicker of its light. All of this sprang from the sharp eyes of a man who simply noticed that the heavens had changed. It is almost poetic that Sakurai's object was not uncovered by accident in some automated survey or massive data pipeline, but by the watchful gaze of a human being who loved the stars. The human element of discovery, the wonder, the curiosity, the persistence, makes the story all the richer. When Sakurai looked up and saw that faint star glowing where none should have been, he could not have known that he was about to rewrite a chapter of stellar evolution. And yet, he did. When the first wave of excitement following Yukio Sakurai's discovery swept through the astronomical community, the natural assumption was simple: a new nova had been spotted. That explanation fit the initial data well enough, and it was what astronomers were used to seeing. But as more telescopes locked onto the object and began peeling away its secrets, it quickly became clear that this was not a nova at all. Something far stranger was happening, something that violated the normal rules of stellar evolution as scientists understood them. The first hints came from spectroscopy, the powerful tool that allows astronomers to decode the light from a star and read the chemical signatures hidden within it. When astronomers examined the light from Sakurai's object, they expected to see the fingerprints typical of a nova, a white dwarf in a binary system, reigniting temporarily as it siphoned matter off a companion star. But the spectral lines didn't match that scenario. Instead, they revealed something eerily different. The star's atmosphere showed signs of being hydrogen-poor but rich in carbon and helium. This was completely at odds with the chemistry of a typical nova, which should display hydrogen features prominently. This mismatch was the first real clue that something extraordinary was unfolding. Astronomers then looked at the object's position in the sky and realized it was at the heart of a known planetary nebula. That fact was chillingly significant. A planetary nebula is the glowing shell of gas ejected by a dying star at the end of its red giant phase. At its center, what remains is a white dwarf, the stellar corpse of a once vibrant star. And sure enough, long before Sakurai spotted it, that central star had been catalogued as just such a faint white dwarf. Here lay the problem: white dwarfs are supposed to be dead. They no longer have the internal nuclear furnaces that power normal stars. After shedding their outer layers and exposing their hot cores, they simply cool and fade for billions of years, drifting ever dimmer into darkness. They do not brighten dramatically. They do not swell up again. They certainly do not look like new stars. And yet Sakurai's object was doing exactly that. To call this puzzling would be an understatement. It was as though a corpse had suddenly sat up in its coffin, taken a deep breath, and begun to speak. Stars are not supposed to do this. The event challenged one of the most fundamental expectations of stellar astrophysics, the irreversible nature of stellar death for sun-like stars. And because Sakurai's object was evolving so quickly, it provided astronomers with no time to carefully build theories first. It demanded immediate explanation. Adding to the strangeness was the timescale. Normally, the processes that govern stellar lives play out over thousands, even millions, of years. The red giant phase, the shedding of the outer layers, the cooling of a white dwarf, all of these happen at a pace far beyond human observation. We can infer them, model them, compare populations of stars at different stages, but we never actually watch one undergo these transformations in real time. Yet Sakurai's object was changing rapidly before astronomers' eyes, its spectrum, brightness, and physical state altering from month to month. It was as if someone had put the evolution of a star on fast forward, compressing millennia of stellar aging into a human timescale. This wasn't just strange, it was unsettling. It suggested that there were rare pathways in stellar evolution that astronomers had only theorized about but never really witnessed. One of those possibilities was the so-called born-again phenomenon, where a white dwarf reignites due to a sudden burst of helium fusion. Such events, called very late thermal pulses, had been predicted in theory. But theory and reality are not the same. Before 1996, only two possible cases had been observed: V605 Aquila in 1919 and FG Sagittarius in the mid-20th century. Both were puzzling, both were difficult to interpret, and neither had been studied as closely as Sakurai's object would be. So when astronomers realized what they were looking at, a profound silence spread across the community. This was no ordinary nova, no binary eruption. This was a resurrection. A star that had exhausted its life, collapsed into a white dwarf, and should have been fading away into oblivion had somehow turned back the clock. It had swollen up again, brightened, and begun behaving like a red giant all over again. It was reversing its death, at least temporarily. The strangeness of this discovery was amplified by the way it blurred categories. In astronomy, classification is crucial. Novae, supernovae, planetary nebulae, white dwarfs, all of these are stages and types that help astronomers organize the chaos of the cosmos. But Sakurai's object defied easy classification. It wasn't a nova, it wasn't a supernova, it wasn't a simple white dwarf, and it wasn't a normal red giant. It was something else entirely. A star resurrected by the violent last gasps of nuclear burning. And perhaps the strangest part of all was that this wasn't just a curiosity tucked away in the past. This was happening right now, as astronomers watched. The star was changing so quickly that teams had to publish urgent updates just to keep up with it. Its brightness rose and fell, its chemical composition shifted, and its surrounding environment transformed dramatically within just a few years. What they were witnessing was not only rare, it was one of the most accelerated transformations ever recorded in a stellar object. The shock was not limited to academic circles. For those who look at the cosmos with a sense of wonder, Sakurai's object seemed almost symbolic. It was a reminder that the universe is not as mechanical or predictable as we might believe. Even in the rigid cycles of stellar birth and death, there are exceptions, moments where the cosmos surprises us with something utterly unexpected. The idea of a star coming back to life captured imaginations around the world, making headlines and drawing attention far beyond the field of astrophysics. In short, what made Sakurai's object so strange was not just what it was, but what it implied, that even the most final processes in the life of a star could, under the right conditions, be reversed. It showed that stellar death might not always be the end, but sometimes, just sometimes, the beginning of something equally remarkable. To understand just how astonishing Sakurai's object really was, we first need to take a step back and look at the normal story of stellar death, the quiet, predictable end that stars like our Sun are destined for. Stars are not eternal. They are born, they live, and they die, and the manner of their death depends largely on one key factor: their mass. The most massive stars die violently, in titanic explosions called supernovae, scattering heavy elements into space and sometimes collapsing into neutron stars or black holes. But smaller stars, the ones more like our Sun, follow a much gentler, though no less dramatic, path toward oblivion. The story begins with hydrogen burning. For billions of years, a star like the Sun lives a steady life on what astronomers call the main sequence. During this long and stable era, the star fuses hydrogen into helium in its core, producing the energy that makes it shine. This is stellar adulthood, steady, unchanging, and long-lived. The Sun, for example, has been in this phase for about 4.6 billion years and will likely remain so for another 5 billion. Stars at this stage are balanced, their inward pull of gravity perfectly countered by the outward push of nuclear fusion. But hydrogen fuel is finite, and eventually, the star begins to run low. When the hydrogen in the core is depleted, the balance is broken. Gravity starts to squeeze the core, making it hotter and denser, while the outer layers respond by swelling outward. This marks the red giant phase, a time when the star expands enormously, its outer atmosphere ballooning to tens or even hundreds of times its original size. If you could live to see the Sun in this stage, its bloated body would swallow Mercury and Venus, and perhaps even Earth. It would shine as a vast, swollen red orb, far cooler at its surface but unimaginably brighter overall. Inside the red giant, new processes take place. With hydrogen exhausted in the core, helium begins to fuse into carbon and oxygen in a series of powerful reactions. These bursts of fusion keep the star alive for a while longer, but they are unstable and cannot last indefinitely. Eventually, the star's outer layers become so unstable that they are expelled into space, forming vast glowing shells of gas and dust. This is the birth of a planetary nebula, a misnamed but beautiful structure that has nothing to do with planets and everything to do with stellar death. The Sun will one day create such a nebula, a glowing cloud of gas stretching light years into space, illuminated by the faint core it leaves behind. At the center of this nebula lies what remains of the star, a white dwarf. This is the hot, dense core that once powered a star, now stripped of its fuel and nuclear fire. White dwarfs are about the size of Earth but contain half the mass of the Sun, making them incredibly dense, so dense that a teaspoon of their material would weigh tons. They shine faintly, not from fusion, but from the leftover heat of their collapsed state. Over billions of years, they cool, slowly fading until they become cold, dark embers known as black dwarfs, though the universe is not old enough for any black dwarfs to exist yet. And that, ordinarily, is the end of the story. A sun-like star is born in a cloud of gas, lives steadily for billions of years, swells into a red giant, sheds its outer layers to form a planetary nebula, and then quietly becomes a white dwarf. It's a one-way journey, an irreversible path. A white dwarf cannot reignite fusion. It cannot swell up again. It cannot return to its youth. Or at least, that is what astronomers thought, until Sakurai's object appeared. That's what makes its story so extraordinary. Sakurai's object should have followed this script to the letter. It had already gone through the red giant phase, already created its planetary nebula, and already collapsed into a white dwarf. By all rights, its fate was sealed. But instead of quietly cooling and fading, it turned back. It came roaring to life in a sudden, unexpected burst of energy, defying the natural flow of stellar time. When astronomers pieced together the true identity of Sakurai's object, one simple fact loomed over all the excitement: this star was supposed to be dead. By the mid-1990s, it had already completed its full evolutionary journey. It had burned through its hydrogen and helium. It had ballooned into a red giant, shedding its outer atmosphere in great gusts of gas and dust that formed a planetary nebula around it. What was left was its core, the compressed, white-hot remnant known as a white dwarf. And once a star becomes a white dwarf, its story should be over. White dwarfs are stellar corpses. They no longer have the nuclear reactions in their cores that give stars their vitality. Unlike the fiery furnaces of main sequence stars, or the unstable burning shells of red giants, white dwarfs are inert. They shine only because they are still extremely hot, glowing with the leftover energy from their earlier life. Over billions of years, they gradually radiate away this heat into space, fading into invisibility. That's it. No more drama. No more life. Just a long, slow cooling into the cosmic night. This is the fate that awaited Sakurai's object. By all the laws of stellar evolution that astronomers had built over decades of observation and theory, the star at the center of its planetary nebula should have been nothing more than a slowly cooling cinder. It should have been quietly dimming, unnoticed except by the occasional catalog entry noting the faint, fading point of light at the nebula's core. It most certainly should not have erupted back into brilliance. Imagine a campfire that has burned out, reduced to a pile of grey ash. You walk away, knowing it can never flare back up again without fresh wood. But then, against all reason, you glance back and see it blazing once more, as if it had reignited itself from nothing. That is the scale of impossibility astronomers faced when Sakurai's object came back to life. To be clear, stars like Sakurai's object are not expected to have any fuel left to burn. By the time a star becomes a white dwarf, it has exhausted its nuclear options. Its core is largely composed of carbon and oxygen, with a thin outer shell of residual hydrogen or helium. Those shells are too weak and too sparse to support sustained fusion. The only path forward should have been a gradual slide into cold obscurity. And yet, instead of cooling, Sakurai's object began to heat up again. Instead of fading, it brightened. Instead of shrinking further, it swelled into something resembling its old red giant self. It was as if time had reversed, as if the arrow of stellar evolution had bent backward upon itself. That was what made it so shocking. The universe does not hand out second chances, and yet here was a star that seemed to have found one. For astronomers, this was deeply unsettling. If a white dwarf could return to life, even temporarily, it meant that the standard model of stellar death was incomplete. While the overall life cycle of stars remained sound, there were evidently rare exceptions, strange loopholes in the cosmos that allowed for this bizarre rebirth. What should have been a quiet, unremarkable ember in the sky had turned into one of the most important astronomical laboratories of the century. Sakurai's object should have been invisible to all but the most powerful telescopes, an afterthought in the grand drama of the galaxy. But instead, by some twist of fate, it became a beacon, its second life outshining the certainty of its supposed death. And because its transformation happened so quickly, it forced astronomers to rewrite their expectations not just about stellar evolution, but about the very nature of time in the cosmos. Normally, stellar change is so slow that human lifetimes mean nothing to it. But here, in the case of Sakurai's object, Entire phases of evolution unfolded in the span of just a few years. The universe had staged a cosmic resurrection, and no one was prepared for it. The story of Sakurai's object pivots on one of the strangest, rarest, and most hauntingly beautiful phenomena in stellar astrophysics, the born-again star. At first glance, the very phrase sounds like poetic exaggeration, a metaphor borrowed from human experience. But in astronomy, it is literal. A born-again star is exactly what it sounds like, a dead star that suddenly flares back to life, as if refusing the finality of its cosmic fate. To understand this, recall what a white dwarf really is. It is the stripped-down skeleton of a star. It no longer possesses the blazing nuclear furnaces that powered its earlier life. Its hydrogen is mostly gone. Its helium has largely been spent. What remains is the carbon-oxygen core, glowing faintly from residual heat. In normal circumstances, that should be the end. But every once in a while, something deeply improbable happens. In a tiny fraction of stars, so rare that only a handful have ever been seen, the dormant white dwarf manages to reignite. Nuclear fusion, not in its core, but in a surrounding shell of helium. This is the heart of the born-again phenomenon, a very late thermal pulse. A burst of helium burning erupts in the thin layer still clinging to the star, releasing a sudden, violent surge of energy. That outburst forces the star's outer layers to expand again, swelling outward until the white dwarf transforms, for a brief second life, into something resembling a red giant. It is a cosmic illusion of resurrection. The star does not return to its former glory permanently, nor does it regain the decades or millennia it once had ahead of it. Instead, it retraces part of its evolutionary path in fast motion, as if the universe itself had decided to rewind the tape. A star that should have only been cooling and fading swells into brightness, reignites fusion, and begins acting as though it were once again in its giant phase. This phenomenon had been theorized before astronomers ever saw it. In the models of stellar evolution, it was predicted that some white dwarfs might still carry enough helium in their outer shells to experience one last surge of burning. These predictions suggested that the process could happen long after the planetary nebula had formed, perhaps tens of thousands of years after the initial death throes. But until the 20th century, evidence for this was scant and uncertain. Astronomers had hints, possible candidates, maybe even a couple of faint historical examples. Yet no one had ever been able to observe one so closely, and certainly not with the technology available in the modern age. And then came Sakurai's object in 1996. This star, once a faded white dwarf in the constellation Sagittarius, suddenly reignited in just such a helium flash. The burst of fusion energy swelled it back up into a red giant-like state, earning it the title of a born-again star. For the scientific community, this was electrifying. It wasn't just a confirmation of theory, it was the rarest kind of laboratory, a real-time, observable resurrection of a stellar corpse. Part of what makes the born-again phenomenon so astonishing is the speed. Stellar evolution normally crawls along at a glacial pace. To watch stars evolve, astronomers often have to compare thousands of different stars at different stages, stitching together a kind of time-lapse from across the galaxy. But in a born-again star, evolution happens on a timescale of months to years. The expansion, the changes in chemistry, the shedding of material, all of it unfolds in real time, visible within the span of human lifetimes. It is the astrophysical equivalent of watching a mountain rise from the sea in the course of a single evening. For astronomers in the late 1990s, Sakurai's object was like lightning in a bottle. It provided a living example of a process that had been relegated to theory. They watched as its atmosphere changed composition, its light brightened, and its outer layers thickened. They tracked its transformation into a carbon-rich, hydrogen-poor object, all the hallmarks of the born-again phase. And because it unfolded so rapidly, they were able to catch every stage of the resurrection, something no one had ever seen with such clarity before. The born-again phenomenon also carried profound implications. If stars could reignite long after death, even temporarily, then stellar death was not as final or as predictable as textbooks suggested. It reminded astronomers that the cosmos is filled with edge cases, rare exceptions that prove the rules are more flexible than we imagine. These exceptions are like cracks in the cosmic script, moments when the universe whispers, "Not everything is as it seems." Of course, the born-again phase does not last forever. It is a fleeting twilight, a swan song rather than a true rebirth. After swelling and burning briefly, the star will once again shed its layers and collapse back into a white dwarf. In a sense, it dies twice. But for the short duration of its second life, it shines with a brilliance that is all the more beautiful for its rarity. Sakurai's object is perhaps the most famous example of this phenomenon precisely because of its timing. Its rebirth happened at a moment when humanity had the tools, spectroscopy, space-based telescopes, infrared observatories, to study it in exquisite detail. And the fact that it was discovered not by a massive institutional survey, but by an amateur astronomer in Japan, made the story all the more remarkable. The heavens had chosen to reveal one of their most guarded secrets, and humanity was ready to watch. At the heart of the born-again phenomenon lies a mechanism both violent and elegant, the final helium flash, also known as a very late thermal pulse. This is the cosmic spark that briefly resurrects a dead star, transforming a faint, cooling white dwarf into a swelling giant once again. To understand how extraordinary this is, we need to peer inside the dying embers of a star and trace the physics of what happens when nuclear burning unexpectedly restarts in its ghostly core. When a sun-like star exhausts its hydrogen and helium fuel, it sheds its outer layers, leaving behind a white dwarf. But the death is not always perfectly clean. Some white dwarfs retain a thin layer of helium surrounding their carbon-oxygen cores, buried under a thin shell of hydrogen. Normally, this helium is inert. It just sits there, slowly radiating heat into space as the white dwarf cools. But under rare conditions, this helium layer can reignite. Here is where the flash comes in. Deep inside the shell, the helium may become dense and hot enough to trigger nuclear fusion once again. But because this layer is not stabilized by the same pressure and energy balance that regulated the star during its main sequence life, the fusion doesn't start gently. It ignites catastrophically, like a match dropped into a powder keg. In an instant, the dormant white dwarf erupts with a helium shell flash, releasing an immense burst of energy. This sudden surge forces the white dwarf's outer layers to expand. The star, which had been small and compact, no larger than Earth, suddenly swells to giant proportions, puffing up into a bloated, luminous body that resembles its earlier red giant stage. To an observer, it looks as though the star has rewound its life cycle, turning back into a giant even though it had already died once. This is why Sakurai's object seemed so strange in 1996. It wasn't a new star being born, but a stellar corpse bloating outward again under the shock of renewed fusion. The process is short-lived compared to the long life of a star. In most cases, the helium flash causes the star to undergo a turbulent phase of rapid changes. It throws off huge amounts of material into space, often rich in carbon and other heavy elements created in its nuclear forges. This carbon-laden dust can obscure the star in visible light, making it seem to dim dramatically after its initial outburst. Meanwhile, the star's surface chemistry transforms. The hydrogen, which had already been mostly shed, becomes vanishingly scarce, leaving behind an atmosphere dominated by helium and carbon. These fingerprints are exactly what astronomers saw in Sakurai's object after 1996. The physics of the helium flash is astonishingly complex, involving the delicate balance of pressure, temperature, and degeneracy in the star's thin shell. White dwarfs are supported by electron degeneracy pressure, a quantum mechanical effect that allows matter to resist collapse even without fusion. But when fusion restarts in the shell, that balance is disrupted, driving an expansion. That mimics the swelling of a red giant. Unlike the Sun's gradual evolution, this expansion happens in fast forward. What takes millions of years in a normal stellar life can happen in just decades, or, in Sakurai's case, mere years. To astronomers, the final helium flash is both a blessing and a rarity. It provides a direct look at stellar interiors in motion, showing processes that are usually hidden from view. In fact, Sakurai's object allowed scientists to test long-standing models of late thermal pulses, a theoretical prediction that had been sitting in textbooks without much observational confirmation. When Sakurai's object flared back to life, it was as though the cosmos had finally staged the experiment for us to witness. But it is important to emphasize how precarious this second life really is. The star does not gain infinite new fuel. It cannot sustain this rebirth indefinitely. After the helium flash subsides, the star will once again shrink back, shedding its remaining layers until all that is left is, once again, a white dwarf. In essence, it dies twice. First in the normal way, then in this spectacular, violent encore. Sakurai's object gave us front-row seats to this encore. When Yukio Sakurai saw his new star in February 1996, what he was really witnessing was a white dwarf undergoing its final helium flash, suddenly inflating like a cosmic balloon. To the untrained eye, it looked like the universe had given birth to a star. But in truth, it was the brief resurrection of a stellar corpse, a light show born of one last convulsion in the star's nuclear heart. This mechanism, though rare, has profound implications. It explains why some planetary nebulae appear to have unusually rich carbon content, why some central stars seem chemically peculiar, and why stellar evolution, for all its predictability, can sometimes throw astonishing curveballs. The final helium flash is nature's way of showing us that even in death, stars can still surprise us. If the universe has taught us anything, it is that rarity amplifies wonder. Stars are countless, hundreds of billions in our galaxy alone, yet the number of born-again stars we have ever witnessed can be counted on one hand. That's how uncommon this phenomenon is. In all of recorded human history, only a few examples have been convincingly identified, and none have been observed as vividly and dramatically as Sakurai's object in 1996. To grasp the significance of this, we need to look at why such events are so rare in the first place. The evolutionary path of sun-like stars is generally well mapped. From main sequence to red giant to white dwarf, the vast majority of stars follow a predictable route with only minor variations. A born-again event, by contrast, requires a very specific chain of conditions to occur. 1. The star must retain just enough helium in its shell after becoming a white dwarf. 2. The timing of the thermal instability must be extremely late, long after the planetary nebula has already been cast off. 3. The flash must be strong enough to reignite helium burning, but not so strong that the star is completely disrupted. It is the cosmic equivalent of threading a needle blindfolded, underwater, while the needle itself is in motion. The odds are staggeringly slim. Most white dwarfs never experience this. They simply cool and fade in silence, as physics dictates they should. This is why astronomers had, before Sakurai's object, seen only two potential cases: V605 Aquila, which flared into view in 1919, and FG Sagittarius, which began showing strange evolutionary behavior in the late 19th and 20th centuries. Both were unusual, both hinted at this process, but neither provided the clarity, speed, and accessibility that Sakurai's object delivered. By the time modern instruments could study them properly, their critical moments had already passed or unfolded too slowly to offer conclusive evidence. Sakurai's object was different. It erupted into brilliance at the perfect moment in astronomical history, when humanity had the tools, and the fortune, to capture its every detail. Think of the odds another way. At any given moment, across the Milky Way's 400 billion stars, countless stellar deaths are unfolding. Planetary nebulae are forming, white dwarfs are cooling, supernovae are exploding. Yet born-again events? Perhaps a few per century in an entire galaxy, if that. And of those, only a fraction occur in places where Earth's astronomers can actually detect them. The fact that one occurred in 1996, in a relatively nearby system only 20,000 light-years away, was nothing short of a cosmic gift. For professional astronomers, the rarity of such events meant urgency. They knew from the very beginning that this was not something that could be put off or studied at leisure. Sakurai's object was changing so quickly, evolving on human timescales, that every week and every month of data was precious. If they missed a stage, they might never see it again, not just in their lifetimes, but in the lifetimes of generations to come. This sense of fleeting opportunity drove a global campaign of observation. Hubble was directed toward it. Infrared telescopes were trained on it. Ground-based observatories around the world coordinated to catch every flicker of its light. The astronomical community understood that they had won a lottery ticket, one they could never expect to win twice. The rarity also deepened the philosophical awe of the discovery. For centuries, humanity has watched the stars, charted their movements, and built elaborate theories of their lives and deaths. Yet only 3 times in all of recorded history has humankind actually witnessed a star return from the brink of death. To see such an event is to be reminded not only of the vastness of the universe, but also of how small and brief our own window of observation is. The stars live for billions of years. Our lives span decades. And yet, by some extraordinary chance, our tiny moment in cosmic history aligned with one of the rarest spectacles the universe has to offer. Sakurai's object, then, is not just scientifically significant, it is statistically miraculous. A white dwarf's helium shell must flare at precisely the right time, in precisely the right way, and in precisely the right place for us to see it. The fact that it happened in 1996, and was caught by the careful eye of Yukio Sakurai, is something astronomers still marvel at to this day. It is no wonder that the event became a cornerstone in the study of stellar evolution, and why Sakurai's object remains a household name among astronomers more than 2 decades later. To put it simply, stars die all the time, and stars are born all the time. But stars being born again? That is almost unheard of. Sakurai's object is one of the very few cosmic phoenixes we have ever witnessed, a star that, against all odds, rose from its own ashes. When Sakurai's object startled astronomers in 1996, it felt like the universe had played a trick, handing back life to a star that had already died. But as shocking as it wasn't entirely without precedent. In fact, 2 other stars in the historical record, V605 Aquila and FG Sagittarius, had shown strangely similar behavior. They, too, seemed to undergo rebirths, giving astronomers tantalizing, though incomplete, glimpses of what would later be recognized as the born-again phenomenon. Sakurai's object was not the first hint of this cosmic trick, but it was the first time humanity caught it in crystal-clear detail. V605 Aquila, the mysterious outburst of 1919. The story begins in the constellation Aquila, the Eagle, in the year 1919. Astronomers detected what appeared to be a nova, a new star suddenly flaring into view. This object, later named V605 Aquila, quickly caught attention because its behavior was odd. Unlike most novae, which brighten and then fade according to well-understood nuclear processes on the surface of a white dwarf in a binary system, V605 Aquila's spectrum and evolution didn't quite fit the template. It brightened significantly, then dimmed, then brightened again. Over time, astronomers realized it wasn't a classical nova at all. Instead, it seemed to be a solitary star undergoing profound internal changes. Later analysis of its light and chemical composition revealed an atmosphere stripped of hydrogen and rich in helium and carbon, the exact kind of profile expected from a final helium shell flash. Even more compelling, V605 Aquila sits at the center of a planetary nebula, Abell 58. That nebula is the corpse shroud left behind from the star's first death. Yet here was the star itself, in the middle, clearly active again. By the late 20th century, as astronomers pieced together stellar evolution theory, they realized that V605 Aquila was likely a born-again star, a forerunner to what would be seen decades later with Sakurai's object. But back in 1919, the tools weren't available to study it properly. Photography was limited, spectroscopy was crude compared to modern standards, and infrared astronomy, crucial for peering through the carbon-rich dust such stars produce, did not yet exist. Much of the critical detail was lost. V605 Aquila faded behind thick clouds of dust not long after its outburst, leaving astronomers with more questions than answers. FG Sagittarius, the slow transformation. If V605 Aquila was an incomplete glimpse of the born-again process, FG Sagittarius was like watching one unfold in slow motion. Located in the constellation Sagittarius, FG Sagittarius had been catalogued in the late 18th century as a fairly ordinary hot star. But by the late 19th century and into the 20th, astronomers began noticing something unusual. FG Sagittarius was changing. Unlike V605 Aquila or Sakurai's object, which erupted into brightness over months or even weeks, FG Sagittarius evolved gradually, over decades. It cooled, expanded, and shifted from the appearance of a hot central star of a planetary nebula to something more like a cool giant. Its spectrum altered dramatically, its brightness fluctuated, and it began to exhibit the same carbon-rich, hydrogen-poor atmosphere characteristic of a helium shell flash. This was a puzzle. Stars don't change that quickly, or at least, they're not supposed to. For a long time, astronomers debated whether FG Sagittarius was simply a peculiar variable star, or something more exotic. Only in hindsight, after Sakurai's object appeared, did the picture snap into focus. FG Sagittarius, too, was a born-again star, just one undergoing the process far more slowly, on a timescale that spanned generations. The value of precedents. Both V605 Aquila and FG Sagittarius gave astronomers crucial hints that the textbooks weren't complete. They showed that stars could undergo late thermal pulses, reigniting briefly after death. But neither case provided the clarity needed to refine theory. V605 Aquila was too fleeting and poorly observed. FG Sagittarius was too slow and ambiguous. That's why Sakurai's object was so electrifying. When Yukio Sakurai stumbled upon his new star in 1996, astronomers already had these precedents in their memory. They knew such things might happen. They had seen tantalizing hints in Aquila and Sagittarius. But this time, with modern telescopes, spectroscopy, and infrared detectors, they could capture every stage in real time. Sakurai's object was the missing link that confirmed the born-again hypothesis beyond reasonable doubt. It is often said that science advances in steps: observation, hypothesis, confirmation. V605 Aquila was observation. FG Sagittarius was hypothesis. And Sakurai's object was confirmation. Together, they formed a chain of evidence stretching across a century, showing that while born-again stars are incredibly rare, they are real, and they are some of the most astonishing phenomena in all of astrophysics. In early 1996, the quiet constellation of Sagittarius suddenly had a new sparkle, a point of light where there had been nothing before. To the untrained eye, it would have seemed like a star had been born, suddenly blazing into view among the crowded star fields of the Milky Way. This was the moment when Sakurai's object first announced its presence to humanity. What observers saw was a star that defied expectation, brightening rapidly, altering its appearance week by week, and revealing a cosmic drama that astronomers would come to call nothing less than a stellar resurrection. First impressions: a nova that wasn't. When amateur astronomer Yukio Sakurai spotted the object in February 1996, it appeared as though a new star had sprung into existence. At first glance, it resembled a nova, the well-known explosion caused when a white dwarf in a binary system undergoes runaway nuclear fusion on its surface. Novae flare up quickly, shining for a few weeks or months before fading back into obscurity. But astronomers quickly realized this object was different. Unlike most novae, which are often detected at magnitudes bright enough for backyard telescopes, Sakurai's object was relatively faint, yet its spectral fingerprints didn't match anything they expected. Instead of showing the hydrogen-rich signatures common in novae, the star exhibited a strange hydrogen deficiency. It looked less like a newly born fireball and more like an aged star revisiting an earlier phase of its life. This peculiarity immediately raised eyebrows. Why was it so different? Why did it lack hydrogen, the most abundant element in the universe? And most of all, why had a supposedly dead star suddenly brightened, as if coming back to life? A sudden brightening. Between February and April of 1996, Sakurai's object brightened dramatically. It went from being an almost invisible point of light to a star that amateur astronomers could easily detect with modest telescopes. For professionals, this was the equivalent of watching a ghost materialize in real time. Stars don't typically change so quickly, at least not in ways that are visible from Earth. The sudden rise in brightness made it feel as though astronomers were witnessing something urgent and fleeting, something that demanded immediate attention. In just a few months, Sakurai's object rose to about magnitude 11, not visible to the naked eye, but strikingly bright against the crowded backdrop of Sagittarius for those who knew where to look. Its location, near the rich star fields of the Milky Way's central bulge, made it both a challenge and a thrill to observe. Amateur astronomers flocked to their telescopes, while professionals scrambled to allocate time on major observatories. Rapid evolution, changing before our eyes. What made the event especially remarkable was how quickly the star evolved in appearance. Most stars take thousands or millions of years to change noticeably. Sakurai's object changed in a matter of weeks. Its spectrum shifted, its brightness fluctuated, and its atmospheric properties began to transform with startling speed. Observers noted that it seemed to be cooling rapidly, moving from a hot, blue-white state towards something resembling a swollen, cool red giant. Normally, such a transformation would take millennia. Here, it was happening fast enough that astronomers could see differences from one observing session to the next. This was the first true confirmation that they weren't looking at a nova at all. Something stranger, something far rarer, was unfolding before their eyes. A star seen reversing time. As the months passed, Sakurai's object began to look more and more like it had turned back the clock. Its spectrum began to match that of a red giant, despite the fact that it had already gone through that phase long ago. To astronomers, it was as if the star had pressed rewind on its life cycle. It wasn't a newborn star at all, it was a dead star coming back to life, briefly resurrecting the stage of its youth. For the astronomical community, this was breathtaking. They were not just reading history in the fossil record of starlight, they were watching it unfold in real time. It was like stumbling across a time-lapse of a flower blooming, except the flower was 20,000 light-years away and billions of years old. Public and professional excitement. The astronomical community buzzed with excitement. Scientific papers began appearing rapidly, each trying to interpret what was happening. Was it a nova-like event? A peculiar variable star? Or could it be something entirely new? Amateur astronomy magazines reported the story widely, and star watchers around the globe added Sakurai's object to their nightly observing targets. At professional observatories, there was an almost palpable sense of urgency. Every telescope capable of imaging or spectroscopy was aimed at Sagittarius. Hubble joined the campaign, providing high-resolution imagery of the object and its surrounding nebula. Infrared telescopes tracked its heat signature, while spectrographs dissected its chemical composition. The result was an unprecedented flood of data on a stellar rebirth. A cosmic performance caught at just the right time. What observers saw in 1996 was nothing short of miraculous. A faint, forgotten remnant in the galactic bulge had flared into brilliance, masquerading as a newborn star while actually reenacting an earlier phase of its life. It was as though the cosmos had staged a performance, lifting the curtain on a stellar drama that few had ever seen before, and it had chosen the one moment in human history when technology was advanced enough, and the human eye sharp enough, to capture it. Astronomers knew they were witnessing a once-in-a-lifetime event. And as the months unfolded, the show only grew stranger. The star would continue to evolve at breakneck speed, dimming, swelling, and shrouding itself in dust, rewriting the rulebook of stellar behavior before their very eyes. When most people think about stars, they imagine timelessness. Stars are ancient, patient furnaces of nuclear fusion, changing only on scales so vast that human lifetimes seem like flickering sparks by comparison. A star like our Sun, for example, takes billions of years to move from one evolutionary stage to the next. Even once a Sun-like star exhausts its hydrogen, swells into a red giant, and finally dies, those transitions are still spread over hundreds of thousands or even millions of years. From Earth, no one expects to see a star truly change before their eyes. And yet, that's exactly what happened with Sakurai's object in 1996 and the years that followed. Its transformation unfolded not over millennia, but over mere months and years. To astronomers, this was the equivalent of stumbling across a time-lapse video of stellar evolution, except the video was playing out in real time, across the skies of Sagittarius. From hot white dwarf to cool giant, in record time. Before its rebirth, Sakurai's object was the core of a dead star, a hot white dwarf surrounded by a planetary nebula, quietly cooling as it should have for eons. But once the final helium shell flash was triggered deep within, the star swelled outward rapidly. Normally, when a star transitions back toward giant-like behavior, the expansion of its outer layers would take thousands of years. Yet for Sakurai's object, this happened in just a few years. Its effective surface temperature plummeted, its spectrum changed, and it went from looking like a hot, faint stellar ember to a bloated, cool, luminous star. By late 1996 and into 1997, astronomers were shocked to find that its spectral type resembled that of a red giant, even though they knew it had already been a red giant long ago. This was not supposed to happen, at least not so quickly. The physics behind the helium shell flash was powerful enough to compress stellar time, condensing what should have been a slow metamorphosis into a rapid-fire sequence. Observable shifts month by month. What made Sakurai's object so extraordinary was the speed of its change. Astronomers could see noticeable differences within months, something that almost never happens in stellar astrophysics. A brightness changes. The star brightened quickly after its discovery, peaked, and then began a series of irregular fades as it built up carbon-rich dust in its outer atmosphere. A temperature drops. Spectroscopic observations showed its temperature falling far faster than stellar models predicted. Within just a few years, it went from tens of thousands of degrees Kelvin down to only a few thousand, a transition that should take millennia. A chemical shifts, the hydrogen lines in its spectrum grew weaker, while helium, carbon, and other heavy elements became more prominent. The composition of its atmosphere was transforming visibly, in real time. To put this in perspective, imagine watching a caterpillar cocoon itself, transform into a butterfly, and emerge, except instead of waiting weeks, the whole process happens in hours. That was Sakurai's object in the eyes of astronomers, a natural metamorphosis, but one running at impossible speed. Evolution faster than models predicted. The rapid evolution of Sakurai's object presented a problem. Existing theoretical models of stellar evolution simply couldn't keep up. Late thermal pulses were predicted in textbooks, yes, but they were expected to unfold over thousands of years. What astronomers witnessed in the 1990s was like watching the theory on fast forward. This forced astrophysicists to revisit and refine their simulations. The data showed that under certain conditions, the outer layers of a white dwarf can respond almost explosively to a helium shell flash, ejecting material and altering the star's physical properties in just a few decades, or even less. Sakurai's object wasn't just unusual, it was a challenge to the very equations used to describe stellar life cycles. A universe on human timescales. One of the most extraordinary aspects of this rapid evolution is that it brought cosmic timescales into human reach. Normally, the great dramas of stellar birth and death are too slow for us to watch directly. We study them through snapshots, one star caught at this stage, another at that stage, and we assemble the pieces into a timeline. But with Sakurai's object, we didn't need a patchwork. We could watch the story unfold, frame by frame, in real time. It was as though the universe had paused to give humanity a live demonstration of stellar physics, compressing millennia into a few fleeting years. For many astronomers, this was more than exciting, it was humbling. The cosmos, usually indifferent to human timescales, had offered them a rare moment of immediacy, a foreshadowing of dust and darkness. The rapid evolution of Sakurai's object didn't stop with its expansion into a giant-like state. The changes set the stage for the next dramatic phase, the sudden creation of enormous quantities of carbon-rich dust, which would soon cloak the star and hide it from view in visible light. The speed of this transformation, from dazzling rebirth to self-obscured obscurity, was just as shocking as the initial flare. Astronomers had caught a star in the act of rebirth, but they would soon have to switch tools and strategies to continue observing it, as the dust grew thicker and the visible light faded away. When Sakurai's object first lit up in 1996, it seemed like a ghost star had returned to life, glowing brightly in the constellation Sagittarius. But just as quickly as it appeared, the star began to veil itself in darkness. Within only a few short years of its rebirth, the object underwent a transformation that both frustrated and fascinated astronomers. It started producing thick clouds of carbon-rich dust that eventually blotted out its light in the visible spectrum. This wasn't a subtle change. It was dramatic, almost theatrical. Imagine an actor stepping into the spotlight, delivering the first act of a performance that has the audience on the edge of their seats, and then suddenly drawing a heavy curtain across the stage. That was Sakurai's object in the late 1990s. Bright, mysterious, and then swallowed up in its own homemade shroud of dust. The star begins to smother its own light. In 1997, astronomers noticed that the light from Sakurai's object was starting to diminish in the optical range. At first, the dimming was gradual, but soon the decline accelerated. By 1999, the star had become so faint in visible light that even large ground-based telescopes struggled to detect it. This was not due to the star's nuclear engine shutting down. Instead, the culprit was dust, vast amounts of carbon-rich soot forming in the outer layers of the star's atmosphere. The newly reborn star had expanded, cooled, and become unstable, allowing carbon atoms to bond together and form microscopic grains. These grains began to clump into larger particles, creating a dense cocoon that absorbed and scattered visible light. To an Earth-based observer, it appeared as though the star was fading, disappearing into obscurity. But in reality, it was just hiding behind a veil of its own creation. Why carbon? The chemical fingerprint of Sakurai's object gave away the nature of the dust. Its spectrum showed that the atmosphere was hydrogen-poor but carbon-rich, a telltale sign of the final helium shell flash that had reignited its core. When helium fusion resumes inside such a star, it dredges up heavy elements like carbon and oxygen from the stellar interior and mixes them into the outer atmosphere. Without hydrogen dominating the chemical balance, carbon atoms can pair up and form molecules like C, and eventually condense into solid soot grains. This made Sakurai's object resemble an extreme version of carbon stars, giant stars known for their red color and carbon-laden atmospheres. But here, the process was happening much faster and more dramatically, producing enough dust to effectively snuff out the star's visible light in less than a decade. The light curves collapse. Astronomers tracked the brightness of Sakurai's object carefully through the late 1990s. What they saw in its light curve was nothing short of astonishing. In 1996, the star was bright enough to be monitored easily through small telescopes. By 1998, it had started to decline sharply in visible brightness. By 1999, it had essentially vanished from optical view, as if it had been switched off. To the casual observer, it might have looked as if the star had died again. But in reality, it was undergoing an intense phase of dust formation that masked its true energy output. The blackout paradox. What's fascinating is that while the visible light disappeared, the star itself didn't stop radiating energy. Instead, the dust absorbed the optical photons and re-emitted the energy at infrared wavelengths. This created a paradoxical situation. To optical telescopes, Sakurai's object looked dead and dark. But to infrared instruments, it glowed brilliantly, surrounded by a warm, dusty envelope. It was as though the star had stepped out of the visible spotlight and continued its performance in a different theater, one that required new technology for humans to see. Astronomical déjà vu are coronæ borealis stars. The behavior of Sakurai's object bore some resemblance to a class of rare variable stars known as a coronæ borealis stars. These stars, too, are hydrogen-poor and carbon-rich, and they are notorious for producing sudden, deep fades when carbon dust forms in their atmospheres. But Sakurai's object was far more extreme. Whereas a CRB stars fade and then recover as dust clears away, Sakurai's object seemed intent on hiding itself almost permanently. Its fade was deeper, longer, and far more dramatic. The aesthetic of disappearance. There is a poetic element to this phase of Sakurai's object's life. After coming back to life in a spectacular burst of brightness that caught the world's attention, the star immediately began to cloak itself in darkness, retreating behind curtains of carbon. It's as though the cosmos was reminding us, stars may reveal their secrets, but only briefly, and only on their own terms. Just when astronomers thought they had a clear window into a stellar rebirth, the object slammed the shutters closed. The curtain falls, but the play continues. By the end of the 1990s, Sakurai's object was almost entirely invisible in optical light. To casual observers, it seemed as though its story had ended. But for astronomers, this was only the beginning of a new chapter. The thick dust, while frustrating, also offered a new opportunity. A chance to study how stars enrich the galaxy with carbon and heavy elements. The soot grains being produced by Sakurai's object were precisely the kind of material that eventually drifts into interstellar space, seeding future generations of stars and planets. In this way, the star's disappearance wasn't just a retreat, it was also an act of cosmic creation. When Sakurai's object first began its dramatic fade from view in the late 1990s, many casual skywatchers assumed its show was over. In visible light, it appeared to vanish, swallowed by the very dust it had produced. But professional astronomers knew better. They understood that light, like a symphony, plays in many different registers. Just because the visible notes had gone silent didn't mean the music had stopped. It had merely shifted to another range, the infrared. To keep tracking Sakurai's object, astronomers had to abandon traditional optical telescopes and instead rely on infrared detectors, which could see through the thick soot that cloaked the star. What followed was a remarkable second act in the story of this reborn star, one that could only be told in wavelengths invisible to the human eye. Why infrared? The dust that Sakurai's object produced was primarily carbon-rich soot, efficient at blocking visible light. When photons in the optical range hit these grains, they were absorbed and scattered, effectively dimming the star until it disappeared. But that absorbed energy didn't vanish. The dust grains themselves warmed up, glowing with thermal radiation. The cooler the material, the longer the wavelength of light it emits. For dust at a few hundred degrees Kelvin, the radiation shifts into the infrared. Thus, while optical telescopes saw only darkness, infrared instruments revealed a glowing cocoon of dust surrounding the hidden star. To astronomers, this was like putting on night vision goggles in a pitch-black room. Suddenly, the unseen came alive. The transition to infrared monitoring. By 1999, optical telescopes had little more to offer. That's when the baton passed to infrared observatories, both ground-based and space-based. Facilities like the Infrared Space Observatory, ISO, the Spitzer Space Telescope, a few years later, and ground-based instruments equipped with sensitive infrared cameras became crucial to monitoring Sakurai's evolution. Infrared observations revealed that while the star had dimmed catastrophically in visible light, its infrared brightness surged. The dust was re-radiating the energy it absorbed, making Sakurai's object appear like a warm ember hidden beneath thick smoke. Instead of fading into obscurity, the star had simply shifted its glow into a new register. What the infrared showed. Infrared monitoring provided astronomers with a treasure trove of insights into the reborn star's strange behavior. A dust shell structure, infrared spectra showed clear evidence of a rapidly forming dust shell around the star. By analyzing the emission, scientists could estimate the size and density of the grains. At temperature drops, infrared data confirmed that the star's surface temperature had plummeted from tens of thousands of degrees to just a few thousand in a handful of years, a staggering change by stellar standards. Chemical signatures. The dust contained carbon-rich compounds, confirming the star's hydrogen-deficient, helium flash origin. Molecules like acetylene, CH, and polycyclic aromatic hydrocarbons, PAHs, were detected, the same kinds of materials that seed interstellar clouds. An expansion of the dust shell, the cocoon of material was seen expanding outward, driven by stellar winds. This not only dimmed the central star but also hinted at how born-again stars contribute to enriching the interstellar medium. A star hidden but not silent. Through the infrared lens, Sakurai's object appeared as though it had wrapped itself in a thick, carbon-rich blanket. This blanket absorbed its heat and re-emitted it, not unlike how a campfire continues to glow beneath layers of ash. The irony here is beautiful. To optical observers, it looked like the star had died again, just a brief flicker of resurrection before vanishing. But in the infrared, astronomers could see that the star was not only alive but still undergoing rapid and violent changes. The role of space-based observatories. Space telescopes played a particularly crucial role. Infrared wavelengths are notoriously difficult to observe from the ground because Earth's atmosphere absorbs much of that radiation. Observatories like ISO, and later Spitzer, gave astronomers a clear view of Sakurai's object without atmospheric interference. These instruments showed that the infrared light curve, unlike the optical one, was still bright and variable, responding to ongoing changes in the star's atmosphere and dust production. This meant the rebirth story was far from over. Lessons from the infrared window. Without the switch to infrared monitoring, Sakurai's object might have faded into a cosmic footnote, a mysterious star that briefly appeared and then vanished. But infrared astronomy kept the story alive, revealing that the star's second life was continuing behind the scenes. It also demonstrated, once again, how essential it is to observe the universe in multiple wavelengths. Each part of the spectrum tells a different chapter of the same story. In the case of Sakurai's object, visible light gave us the drama of resurrection, while infrared gave us the subtler tale of transformation hidden behind dust. The human parallel. There is something profoundly moving about this. Just as human understanding often requires us to look beyond surface appearances, so too did Sakurai's object demand a deeper gaze. It wasn't enough to watch it with our eyes, we had to extend our vision into the unseen. Only then did the full truth emerge. The star had not ended its show, it had simply shifted stages. The most hauntingly poetic aspect of Sakurai's object is what astronomers have often described as the back-in-time effect. Imagine, for a moment, if a human being nearing the end of their life could suddenly rewind the biological clock and regain the appearance, vigor, and physical state of their younger years, not in a slow and gradual way, but in a startling, almost violent reversal. That is exactly what Sakurai's object did. When Yukio Sakurai first spotted the star in 1996, astronomers quickly realized they were not witnessing the birth of a young star, but rather the sudden rebirth of a dead one. And as it began to evolve, it looked eerily as if the star had wound back the clock of stellar evolution and placed itself once again into a stage it should have left behind thousands, even tens of thousands, of years ago. From white dwarf to red giant, again. To understand why this seemed like such a reversal, we need to recall what Sakurai's object was supposed to be. Before its outburst, it had already gone through the full stellar life cycle of a sun-like star. It had burned hydrogen in its core for billions of years. It had swelled into a red giant, fusing helium and creating heavier elements. It had expelled its outer layers into space, forming a planetary nebula. Its core had been stripped bare, collapsing into a white dwarf, the quiet, fading ember of a once bright star. At this stage, the story should have ended. White dwarfs are the stellar equivalent of cosmic retirees, glowing faintly as they cool over billions of years. But Sakurai's object rebelled against this script. Instead of continuing to cool, it suddenly flared back to life in a late helium shell flash. Nuclear fusion reignited in its core, pumping new energy into the star and causing its outer layers to expand outward once again. In mere years, the white dwarf ballooned back into a red giant-like state, something it should never have been able to do. The illusion of time reversal. From Earth, this process made it appear as though time itself had reversed. Astronomers were essentially watching a white dwarf, a stellar corpse, morph back into a swollen red giant, a stage that normally comes before the white dwarf phase. It was as if someone had rewound a cosmic movie. The planetary nebula that surrounded Sakurai's object stood as evidence of its first death. Yet inside that nebula, the core star was behaving as though its earlier life cycle had returned. Past and present collided in a single object, a shell of death surrounding a star seemingly reborn. This dissonance is what made Sakurai's object such a compelling target. No textbook on stellar evolution, prior to 1996, had prepared astronomers to witness such a striking reversal playing out in real time. How fast the rewind happened. What made the effect even more dramatic was the speed at which it occurred. Normally, the transition from red giant to white dwarf takes thousands to tens of thousands of years. Sakurai's object reversed much of that process in just a handful of years. By the late 1990s, only 3 or 4 years after its initial brightening, the star's spectrum looked strikingly similar to that of a cool, carbon-rich red giant. It wasn't simply mimicking the appearance, it was physically behaving like one, with powerful winds, pulsations, and copious dust production. For astronomers used to working on timescales where change is measured in centuries or millennia, this rapid transformation was breathtaking. It was like watching geological forces unfold at the speed of weather. A star out of place in time. The surrounding planetary nebula provided a stark reminder that Sakurai's object was not truly a young star, but an old one acting strangely. That nebula was the fossil of its first death, glowing faintly in the background, a shell of gas expelled thousands of years earlier. Inside that ancient shell, however, sat a star that now looked for all the world like a newly minted red giant. This juxtaposition made it clear, Sakurai's object wasn't young again, it was pretending to be, as a result of its internal helium flash. The star's behavior gave the illusion of youth, but the evidence of its long life was floating all around it. The human analogy. To make sense of this, many astronomers and science communicators have leaned into metaphor. It was as if an elderly person, already frail and nearing the end of life, suddenly regained the appearance and vitality of a 20-year-old, not by slowing down the aging process, but by literally replaying their life stages. Of course, the process was unstable and unsustainable. Unlike humans, stars cannot keep rewinding forever. The rebirth of Sakurai's object was spectacular, but it was also temporary, a cosmic encore, not an infinite cycle. Why the back-in-time effect matters. This reversal taught astronomers a great deal about stellar evolution. It showed that the late helium shell flash could literally reset a star's outer layers, dredging up new elements and producing a temporary second red giant phase. It also provided a rare, real-time example of how stars can recycle themselves, enriching their surroundings with carbon and other heavy elements. In effect, Sakurai's object wasn't just reliving its past, it was reshaping its future role in the galaxy by producing dust and matter that would someday become part of new stars and planets. The poetic takeaway. Sakurai's object became a reminder that the universe doesn't always obey the neat, linear paths that textbooks suggest. Sometimes, time bends. Sometimes, endings become beginnings again. And sometimes, even the dead find a way to masquerade as the living. For astronomers, it was both confusing and humbling to watch. They were not merely observing a star, they were witnessing the universe toying with the very concept of time. One of the most extraordinary gifts Sakurai's object offered to humanity was the chance to perform what many astronomers called a kind of stellar autopsy in real time. Normally, the life and death of stars play out across timescales so long that human beings can only piece together the story by comparing stars at different stages, like snapshots from different albums. We might look at a red giant here, a white dwarf there, and a planetary nebula elsewhere, then stitch them into a sequence to form a model of stellar evolution. But with Sakurai's object, something different, almost miraculous, happened. We were allowed to watch a star undergo catastrophic and transformative changes in front of our eyes. Why this was so rare? Stellar death is usually a slow, majestic process, spanning tens of thousands to billions of years. Even the final stages, which are violent by astronomical standards, rarely unfold in a time frame that matches human lifespans. Supernovae are exceptions. They explode in a flash of days, but those are massive stars, not the Sun-like variety. For low to medium mass stars, like Sakurai's object, visible changes are supposed to be painfully gradual. But in the case of Sakurai's object, evolution happened so quickly that astronomers could monitor its shifts month by month, even week by week. The star's atmosphere changed, its brightness surged and dimmed, its spectrum morphed, all in timescales so short that scientists could sit at a telescope one year and then return the next to find a completely transformed object. This was unheard of in stellar astrophysics. It was as though a patient on an operating table, whose body had already ceased functioning, suddenly revived and began going through the stages of life again at high speed. And the astronomers, armed with their instruments, had front-row seats to this cosmic autopsy. The unique opportunity for science. The rebirth of Sakurai's object provided astronomers with a priceless observational laboratory for stellar physics. Here was a star exposing the secrets of late thermal pulses. Until Sakurai's object, the theory of final helium flashes was more of a mathematical prediction than something anyone had directly witnessed in action. Now, they had proof. Elemental mixing. As the helium flash dredged up new material, astronomers could watch hydrogen disappear from the surface layers while carbon and helium rose to dominance. That kind of chemical fingerprint had been hypothesized but never observed so dynamically. Dust production. The star showed how rapidly a stellar corpse could pump carbon-rich material back into space, directly demonstrating how stars seed the galaxy with the ingredients for planets, organic molecules, and perhaps even life. Rapid evolution models. Instead of tweaking equations to match static snapshots, astrophysicists could now refine models against time series data, a living case study of stellar death and rebirth. Spectroscopy. The autopsy tools. One of the most important methods for this autopsy was spectroscopy. By breaking down the star's light into its constituent wavelengths, astronomers could identify which elements and molecules were present in its atmosphere and surrounding dust. Before 1996, Sakurai's object had the spectral signature of a fading white dwarf. After the helium flash, however, its spectrum began to resemble that of a carbon-rich red giant. Lines of hydrogen weakened dramatically, while features linked to carbon compounds grew stronger. In essence, the star's chemical makeup was broadcasting its internal changes in real time. This was like opening a cosmic cadaver and watching its organs reorganize themselves. The data was so fresh and so startling that astrophysicists scrambled to rerun their models, now with live evidence guiding them. Watching the universe work. For generations, astronomers had to infer the details of stellar death. They saw planetary nebulae as relics, white dwarfs as remnants, and red giants as bloated beacons. But no one had ever been fortunate enough to watch the transition itself unfold in such a dramatic and compressed timeline. Sakurai's object gave them that chance. It was as if the curtain of time had been pulled aside for a brief moment, letting humanity peek at the otherwise invisible machinery of stellar evolution. Every new observation was like a scalpel cut into the anatomy of the star, revealing not just how it had lived, but how it was dying, and dying twice. The human dimension. It's worth pausing to appreciate just how staggering this was for the scientific community. In the 1990s, Astronomers were not expecting to catch such an event. Most scientists build careers on phenomena that can be studied slowly and patiently: galactic evolution, planetary dynamics, stellar populations. But here, suddenly, was a star throwing a tantrum, changing faster than most research projects could even keep up with. Graduate students and postdoctoral researchers who began studying Sakurai's object in 1996 found that their work was outdated by 1998 because the star had already evolved into a new state. For some, this was exhilarating. For others, it was overwhelming. The pace of discovery was relentless, almost as if the star itself were taunting humanity with how much it could reveal before vanishing again into obscurity. The cosmic autopsy revealed. Through all this, astronomers confirmed several groundbreaking insights. Stars can indeed undergo born-again phases, validating decades of theory. The transformation from white dwarf to red giant can occur in just a few years, a blink in cosmic terms. The chemical makeup of the star's atmosphere can shift radically and rapidly, showing direct evidence of helium burning and hydrogen depletion. Stars nearing the end of life are not passive corpses but can still profoundly shape their environments, enriching their surroundings with carbon-rich dust. These insights were only possible because Sakurai's object had the courtesy, or perhaps the cosmic mischievousness, to let us witness its resurrection and decline in real time. A rare, unrepeatable gift. Astronomers often speak of Sakurai's object with a kind of reverence, as though it were less a research target and more a once-in-a-lifetime chance encounter. Events like this are staggeringly rare. Entire centuries may pass without humanity catching another one in action. And so, in the 1990s and 2000s, the star became one of the most intensely observed objects in the sky, not because it was bright or beautiful, but because it was teaching us lessons about death, rebirth, and the recycling of the cosmos itself. It was, in every sense, a stellar autopsy, but one unlike any before. The patient wasn't entirely dead, the dissection was happening live, and the body kept shifting form as if determined to keep its secrets only half revealed. When astronomers turned their telescopes towards Sakurai's object after Yukio Sakurai's startling discovery in 1996, they noticed something that deepened the mystery and confirmed beyond doubt that this was not a young star being born for the first time. Surrounding the star was a faint, ghostly shell of glowing gas, a planetary nebula. This nebula was the smoking gun, the undeniable evidence that Sakurai's object had already gone through the grand finale of its stellar life once before. The star had lived, swelled up into a red giant, shed its outer layers into space, and collapsed into a white dwarf. In other words, Sakurai's object had already died once. And that surrounding nebula was the tombstone it had left behind. What is a planetary nebula? The term planetary nebula is a bit misleading. It has nothing to do with planets. Early astronomers using small telescopes thought these round, glowing shells looked like the disks of planets, so the name stuck. In reality, a planetary nebula is the outer atmosphere of a dying star, ejected into space when the star can no longer hold onto its layers. For sun-like stars, this stage marks the transition from red giant to white dwarf. The hot core left behind lights up the expanding gas, making it glow in delicate hues of red, green, and blue, depending on which elements are present. These nebulae are often beautiful, butterfly-like or spherical in shape, but their significance goes beyond aesthetics. They are the last breath of a star before it fades into obscurity. Sakurai's nebula as proof of its past. When scientists observed the faint nebula around Sakurai's object, they immediately knew this wasn't a star being born. Young stars do not have planetary nebulae. Only stars that have already gone through the red giant and white dwarf phases create them. That meant that, by 1996, Sakurai's object was not a star on its way up the ladder of stellar life. It was a star climbing back down that ladder, or more accurately, stumbling backwards onto a step it had already left behind. The nebula was silent proof of the star's earlier death and transition into a white dwarf state. The age of the nebula. Astronomers studied the size and expansion rate of the nebula around Sakurai's object to estimate its age. The gas appeared to have been expelled thousands of years ago, during the star's first red giant death. That meant Sakurai's object had been sitting quietly as a white dwarf for millennia, cooling slowly, as expected. Then, in the mid-1990s, something extraordinary happened. A late helium shell flash reignited nuclear fusion and made the star expand back into a red giant-like state. The nebula, already drifting in space for thousands of years, was suddenly illuminated again by its resurrected parent star. It was almost like watching a gravestone suddenly glow, as though the dead had decided to rise again. The contrast between past and present. This planetary nebula created a haunting juxtaposition. On one hand, you had the shell of gas, cold, diffuse, and ancient, marking the star's first death. On the other hand, you had the central star itself, brightening and expanding as though it were young again. This contrast was one of the key features that stunned astronomers. Normally, a planetary nebula surrounds a dying or fading white dwarf. But here, that same nebula surrounded a star that looked like a red giant reborn. It was like finding a skeleton next to a living, breathing body and realizing they belonged to the same person. Why the nebula matters for science. The planetary nebula wasn't just symbolic, it was scientifically crucial. Because the nebula could be studied alongside the star, astronomers could piece together a fuller picture of its life story. The nebula's chemistry told them what elements the star had shed during its first death. Its expansion revealed the timescale of when that death had occurred. Its presence ruled out the possibility that this was a newborn star. Without the nebula, the sudden brightening of Sakurai's object might have been interpreted as some exotic form of star birth or outburst. But with the nebula present, there was no doubt, this was a dead star pretending to be alive again. A cosmic cemetery scene. Visually, it's haunting to think about. Imagine a glowing shell, tens of thousands of times larger than our solar system, drifting quietly in space for millennia, its parent star reduced to a faint cinder at the center. Then suddenly, that cinder flares up, brightens, and swells into a giant again, as if it has clawed its way out of its grave. The nebula around Sakurai's object wasn't just a backdrop, it was the evidence of a life already lived, the stage on which the bizarre born-again performance was playing out. The broader lesson. Planetary nebulae remind us that stars don't die neatly. They cast off their shells, scatter their material, and enrich the galaxy with carbon, nitrogen, and oxygen. These elements go on to form planets, oceans, and even life. In Sakurai's case, its nebula told us that the recycling process had already happened once, and yet the star still had more to give, producing even more carbon-rich dust after its rebirth. It was as if Sakurai's object were doubling down on its role in cosmic evolution, leaving not one but two legacies of enriched material for the future universe. When astronomers studied the atmosphere of Sakurai's object after its astonishing rebirth, they encountered one of the most compelling pieces of evidence that they were witnessing a born-again star. The chemical fingerprints of its surface revealed something that was not at all normal for an ordinary star. Hydrogen, the most abundant element in the universe, and the dominant ingredient in almost every stellar atmosphere, was mysteriously missing. Instead, the star's outer layers had become hydrogen-poor and carbon-rich. This was not just a quirk of chemistry. It was the unmistakable hallmark of a helium flash, the violent event that had caused the star to reawaken in the first place. Why hydrogen matters in stars. To understand why this was so significant, we have to remember what a star is made of. Normal stars, like our Sun, are about 70% hydrogen, 28% helium, and 2% heavier elements. Hydrogen dominates their atmospheres because it is the star's primary fuel. But in Sakurai's object, astronomers found something bizarre. The usual hydrogen lines in the star's spectrum, those bright or dark fingerprints that hydrogen leaves when it absorbs or emits light, were drastically weakened. In some cases, they were almost absent. Instead, the star's spectrum was dominated by helium and carbon features. It was like looking at a car's exhaust pipe and realizing there was no trace of gasoline fumes, only evidence of some exotic, unexpected fuel being burned. The helium flash and atmospheric change. The explanation lies in the final helium shell flash that Sakurai's object experienced. Deep within the star, in the thin shell where helium was still present, runaway nuclear fusion ignited. The helium flash not only released enormous energy but also stirred the star's interior. This process caused convective mixing. Layers of material from the star's interior bubbled upward, while the thin remaining skin of hydrogen on the surface was burned away or buried. In effect, the helium flash scoured the star's atmosphere clean of hydrogen, leaving behind an outer layer rich in helium and carbon. This transformation is what made Sakurai's object appear chemically alien compared to ordinary stars. It was no longer a normal star, but the exposed heart of a stellar corpse laid bare for astronomers to study. Hydrogen-poor, carbon-rich signature. The hydrogen-poor, carbon-rich signature was a smoking gun because it matched exactly what theorists had predicted for born-again stars. Models suggested that during a very late thermal pulse, a white dwarf could briefly swell back into giant form, and its atmosphere would be dominated by helium, carbon, and oxygen, elements forged in the star's earlier life. And indeed, that's what was observed in Sakurai's object. A hydrogen, drastically reduced, sometimes almost absent. A helium, strongly present, indicating helium fusion had been the driving force. A carbon and oxygen, abundant, dredged up from deep inside the star. This was one of the most direct confirmations that the theories of final helium flashes were correct. Comparisons with other born-again stars. The hydrogen-poor, carbon-rich atmosphere of Sakurai's object also linked it with other rare cases of born-again stars, like V605 Aquila and FG Sagittarius. These objects too showed unusual chemical compositions dominated by helium and carbon. But Sakurai's object was unique in how fast these changes happened and how clearly they could be observed in real time. Within just a year or two of its discovery, astronomers saw the star's spectrum shift dramatically as its atmosphere was reshaped by the flash. It was as if someone had peeled back the outer layers of the star, exposing the once hidden core. Why this was important for astronomy? For scientists, the chemical fingerprint of Sakurai's object wasn't just a curiosity. It was direct evidence that stellar interiors and atmospheres interact violently during the final stages of life. It showed that the thin hydrogen skin on a white dwarf could be obliterated, leaving behind a carbon-rich surface. This has profound implications. It explains why some white dwarfs in our galaxy appear hydrogen-poor when most should be hydrogen-rich. It gives insight into how stars contribute carbon and other heavy elements to the interstellar medium. It provides a model for what our own sun might do billions of years from now, when it sheds its hydrogen-rich skin and possibly undergoes a late helium flash. The human angle, a star that defied identity. From a poetic standpoint, the atmosphere of Sakurai's object was like a disguise falling away. For millennia, as a white dwarf, it had worn a thin hydrogen mask. But when the helium flash struck, that mask was ripped off, and the star's true inner nature was revealed. A carbon-rich remnant, the raw product of nuclear furnaces long extinguished. It's almost as if the star had shed the trappings of youth and middle age and finally stood bare, showing the core of what it had always been. For astronomers, this wasn't just data, it was the feeling of being in the presence of a truth the universe rarely exposes. Dust and the atmosphere. There was another consequence of the star's altered atmosphere, dust formation. With so much carbon at the surface, Sakurai's object began to spew carbon dust into space. This dust cloud soon obscured the star's visible light, making it harder to observe except in the infrared. The chemistry of its atmosphere, therefore, didn't just tell scientists what was happening internally, it directly shaped how the star looked to us. The hydrogen-poor, carbon-rich atmosphere became both a signature and a curse. It confirmed the helium flash but also cloaked the star behind an ever-thickening veil of dust. The broader cosmic story. Every time a star like Sakurai's object produces carbon-rich material, it contributes to the building blocks of life in the galaxy. Carbon is the backbone of organic molecules. It is what makes DNA possible, what allows planets to form solid cores, what eventually gives rise to creatures like us. So, in its hydrogen-poor, carbon-rich transformation, Sakurai's object wasn't just rewriting its own story. It was adding another chapter to the larger cosmic narrative of how stars die, how elements are forged, and how the raw ingredients of life are spread across the Milky Way. When astronomers observed the extraordinary rebirth of Sakurai's object, one of the most immediate and haunting questions they asked was, could this happen to our sun someday? The answer, surprisingly, is yes. Not in the near future, of course, but in the unimaginably distant timeline of billions of years. The story of Sakurai's object is not just the tale of an exotic star in Sagittarius. It is, in many ways, a preview of our sun's eventual fate. And by watching this born-again star, astronomers have gained a window into the ultimate destiny of the very star that makes life on Earth possible. The sun's current life stage. Right now, our sun is in the main sequence phase, quietly fusing hydrogen into helium in its core. This stable process has been ongoing for about 4.6 billion years and will continue for another 5 billion years or so. The Sun is middle-aged, and like all main sequence stars of its mass, it is remarkably stable. But nothing lasts forever, not even the Sun. Eventually, the hydrogen in the core will be exhausted, and the Sun will face the same transformation that Sakurai's object once did in its earlier life. The Sun's death process. Here's the simplified timeline of what will happen. 1. Hydrogen exhaustion. The Sun's core will run out of hydrogen, forcing fusion to shift into a shell around the core. 2. Red giant phase. The Sun will swell to enormous size, possibly engulfing Mercury and Venus, and perhaps Earth as well. 3. Helium fusion. For a time, the Sun will fuse helium into carbon and oxygen, producing new heavy elements. 4. Planetary nebula. The Sun will shed its outer layers into space, creating a glowing shell of gas, like the nebula around Sakurai's object. 5. White dwarf. At the center, a hot, dense, Earth-sized white dwarf will remain, the final core of the Sun, slowly cooling for eternity. That's the standard story. For decades, astronomers assumed this was the inevitable and final fate of stars like the Sun. The Sakurai's object twist. But Sakurai's object introduced a shocking twist into this story. Death might not be final. Instead of cooling quietly as a white dwarf, Sakurai's object underwent a late helium shell flash, reigniting nuclear burning, swelling back into a red giant, and producing fresh dust and carbon. In essence, it was reborn for one last act before fading again. This means that when our Sun dies and becomes a white dwarf, it might not stay dead. Thousands or tens of thousands of years later, it could undergo a similar helium flash, flare back to life, and briefly shine as though it had been resurrected. Implications for the solar system. If our Sun experiences such a born-again phase, the consequences for the solar system would be dramatic. By that point, Earth and the inner planets will almost certainly be gone, either swallowed during the red giant phase or rendered barren and lifeless. But the Sun's rebirth could still influence the outer solar system. New outbursts of dust and gas could enrich the outer regions with fresh material. Comets and Kuiper belt objects might be destabilized or altered by the renewed radiation pressure. The Sun's planetary nebula could glow again, briefly lighting up the cosmos as a cosmic ghost. It's a strange thought. Long after humans are gone, long after Earth itself is dust, our Sun might still stage a surprise encore performance in the silent theater of the galaxy. What we learn about stellar evolution. For astronomers, Sakurai's object provided direct evidence that stars like the Sun might not end their lives as quietly as once thought. The born-again phenomenon suggests white dwarfs can be unstable. Even after their main life has ended, under the right conditions, they can erupt again. The Sun's future might be less simple. Instead of a neat transition to a white dwarf, there may be a chaotic and unpredictable rebirth. The recycling of elements continues. A born-again phase allows stars to spew additional carbon and heavy elements into space, seeding the galaxy with even more raw material for future planets and life. The emotional impact. There's something deeply human about imagining our Sun's eventual fate through the lens of Sakurai's object. It's as though the universe is telling us, even stars can stumble, fall, and rise again in strange and unexpected ways. From a poetic perspective, the Sun may one day prove that death is not a single moment but a process, sometimes punctuated by brief flashes of life. Just as Sakurai's object defied its own ending, perhaps our Sun too will briefly burn again, a final gesture before the true silence of eternity. A second chance for the Sun. The key lesson is that Sakurai's object reminds us the Sun may not fade smoothly into cosmic obscurity. Instead, billions of years from now, it might have one last encore, one last chance to shine before disappearing forever. For astronomers, that possibility is thrilling. For us as humans, it's humbling. The very star that gave birth to us may one day reenact the strange rebirth of Sakurai's object, becoming, briefly, a cosmic phoenix before turning to ash. The most breathtaking thing about Sakurai's object was not just that it came back to life, it was how fast it transformed. Stars, by their very nature, evolve on timescales that dwarf human history. Entire civilizations rise and fall while a star makes the smallest of shifts in brightness or temperature. Astronomers spend lifetimes observing stars that barely change at all, relying instead on theory and simulation to reconstruct the cosmic clockwork of stellar evolution. And then along came Sakurai's object, which compressed thousands of years of stellar change into mere months. To astronomers, it was like watching a glacier sprint, a mountain grow in front of your eyes, or a tree age from seedling to ruin in a single season. The normal timescale of stellar change. To understand why Sakurai's object was so shocking, consider the typical pace of stellar evolution. A main sequence stars like the Sun live for billions of years, changing so gradually that the difference between one century and the next is imperceptible. A red giants expand over tens of millions of years, a blink in cosmic terms but still utterly beyond human observation. A white dwarfs cool on timescales of billions of years, slowly fading as embers in the cosmic night. In all these stages, the progression is slow, smooth, and patient. For humans, the only way to understand these changes is through snapshots of many stars at different stages, pieced together like a cosmic jigsaw puzzle. Sakurai's object broke the rules. When Yukio Sakurai discovered the object in 1996, it looked like a typical nova, something that should brighten over weeks and then fade. But instead of behaving like a nova or fading into obscurity, the star continued to evolve at breakneck speed. Within months, its spectrum shifted dramatically. Within a year, it was clear its atmosphere had transformed into a hydrogen-poor, carbon-rich composition. Within a couple of years, the star was shedding vast amounts of dust, obscuring itself in visible light. In less than a decade, it had gone through changes that normally take thousands to tens of thousands of years in stellar models. For astronomers, it was like watching a time-lapse movie of stellar death and rebirth unfolding in real time. The human analogy. To put it into perspective, imagine a person aging not over 80 years but over 8 days. One moment they are in their youth, the next they are wrinkled and frail, then suddenly they return to the vigor of midlife before collapsing again. That is how bizarre Sakurai's object appeared, a star experiencing a full evolutionary cycle at hyperspeed. Why did it happen so fast? The culprit behind this astonishing acceleration was the final helium flash. When the helium shell ignited deep inside the star, it released energy so rapidly that the star couldn't respond in its usual slow, stately fashion. Instead, it swelled, mixed its layers, shed its hydrogen, and spewed carbon dust, all in the astronomical equivalent of an instant. The speed was also influenced by the fact that Sakurai's object was already a white dwarf, a compact star with little mass left. With only thin layers of fuel to ignite, the changes played out much faster than they would in a full-fledged giant star. It was a brief, furious flash rather than a long, drawn-out burn. Astronomers racing against time. One of the most dramatic aspects of this rapid evolution was that astronomers had to scramble to keep up. Normally, stellar research involves patient observation, compiling data over decades or even centuries. But with Sakurai's object, every month brought a new transformation. Telescopes pointed at it had to adapt rapidly, switching from optical to infrared as dust obscured the view. Models of stellar evolution were revised in real time, because the star's behavior was rewriting the textbooks as it unfolded. Researchers who expected to study a stable nova-like event suddenly found themselves chasing an unprecedented stellar rebirth at breakneck speed. For once, astronomy wasn't about the long game, it was about keeping pace with a cosmic event that was changing as quickly as the nightly news. A rare opportunity. The abnormal speed of Sakurai's object's evolution was both a challenge and a gift. It challenged astronomers to explain why a star could change so drastically in mere years, but it also gifted them with a unique laboratory. Instead of piecing together stellar evolution by comparing stars of different ages, they got to watch a single star race through multiple stages of its life. It was like watching all 4 seasons unfold in a single week: spring, summer, autumn, and winter flashing before the eyes of human observers. Why it matters for the Sun and other stars. The Sun will one day die far more slowly, but Sakurai's object proved that white dwarfs are not always stable. Some of them can experience bursts of accelerated evolution that defy normal timescales. This insight forces scientists to reconsider how often stars might undergo such events and whether the Sun could, in theory, also experience a rapid born-again flash. Even if such an event is rare, the fact that Sakurai's object showed us the possibility means stellar death is more complex and less predictable than once thought. The cosmic drama in human time. Perhaps the most striking thing is how Sakurai's object compressed the slow ballet of stellar evolution into a human timescale. For once, astronomers did not need to imagine the life cycle of a star abstractly. They were able to live through it, year by year, and record every stage. It was as though the universe had pulled back the curtain and given humanity a private showing of one of its deepest mysteries, sped up for our benefit, so we could see the normally invisible passage of cosmic time. When Sakurai's object first burst onto the scene in 1996, astronomers knew they had stumbled upon something extraordinary. But what they didn't fully realize at the time was that this was not a one-time show. The rebirth of this star would turn into a decades-long saga, requiring patient and persistent observation to capture its continuing transformation. Even after its initial outburst faded from headlines, astronomers never turned away. For nearly 30 years now, Sakurai's object has been one of the most closely monitored stellar phenomena in the night sky. The need for long-term monitoring. The reason for this obsessive attention is simple. Events like this almost never happen. Sakurai's object offered astronomers a chance to watch stellar evolution unfold in real time, a process that normally spans tens of thousands to millions of years. Missing even a few years of data would mean losing pieces of a story that humanity may never see again. So, from the very beginning, researchers committed to following every twist and turn of the star's journey. The Hubble Space Telescope's role. One of the most important tools in this effort has been the Hubble Space Telescope. Hubble's unparalleled resolution and ability to see in ultraviolet and optical light made it ideal for tracking the faint central star and its surrounding nebula. Our early observations, late 1990s Hubble captured detailed images of the planetary nebula surrounding Sakurai's object, allowing astronomers to map the relics of its first death. A dust obscuration. As the central star became shrouded in carbon-rich dust and faded from view in visible light, Hubble still managed to peer through parts of the haze, offering glimpses of the evolving core. Structural changes. Over the years, Hubble documented how the gas and dust expelled by the star expanded and interacted with the older planetary nebula, creating an evolving cosmic sculpture. Without Hubble, much of this delicate detail would have been lost. Ground-based telescopes joined the effort. But Hubble wasn't the only eye on the star. Ground-based observatories across the world, especially those equipped with infrared instruments, took on a critical role once dust blocked the star's visible light. Our infrared observations, facilities like the Very Large Telescope, VLT, in Chile and the United Kingdom Infrared Telescope, UKIRT, in Hawaii provided long-term data, tracking how the star's energy output shifted into infrared wavelengths. A spectroscopy. By splitting the star's faint light into spectra, astronomers were able to measure its chemical composition over time, noting the decline of hydrogen and the rise of carbon and other heavy elements. A light curves. Regular monitoring from smaller observatories kept track of the star's variability, its brightenings, dimmings, and irregular outbursts. This global cooperation created a continuous timeline of observations, turning Sakurai's object into one of the most well-documented stellar events in history. The importance of patience. Astronomers are still watching, decades later, because the story isn't over. The initial rebirth happened quickly, but the aftermath is playing out slowly, almost like an epilogue to the cosmic drama. At the dust cocoon, today, Sakurai's object remains hidden behind thick dust, invisible in normal optical light. Monitoring its infrared glow is the only way to keep track of what's happening inside. A temperature changes. Observations show that the central star, after swelling into a red giant-like state, has started to heat up again, shrinking back towards something resembling a white dwarf. A nebular interaction. The gas and dust expelled during its rebirth continue to expand outward, colliding with the older planetary nebula from its first death, creating shockwaves and new structures. All of this can only be tracked through long-term commitment. If astronomers had stopped watching after the 1990s, these critical phases of evolution would have been missed forever. Monitoring with new generations of technology. The continued observation of Sakurai's object is also a testament to how astronomy evolves with technology. A Spitzer Space Telescope provided mid-infrared data before its retirement, complementing ground-based efforts. Air Alma, Atacama Large Millimeter Submillimeter Array, in Chile has observed the molecular gas around Sakurai's object, revealing the chemical fingerprints of its evolving atmosphere and dust. A James Webb Space Telescope, JWST, with its powerful infrared instruments, JWST now has the potential to provide the clearest view yet into the dust-enshrouded heart of Sakurai's object, continuing where Spitzer left off. Each new generation of telescope has allowed astronomers to peel back another layer of mystery, ensuring that this cosmic story is preserved in ever-increasing detail. A living case study. What makes Sakurai's object so valuable is that it is a living laboratory of stellar physics. Normally, astronomers are forced to piece together theories from static snapshots of different stars in different phases. But here, they get to watch a single star change in real time. By monitoring it for decades, they are building a complete, continuous record of a rare stellar event, something future generations of astronomers will study for centuries. Humanity's long vigil. There is something poetic about this prolonged monitoring. A single human lifetime is just long enough to watch Sakurai's object rise, transform, and slowly fade again. For once, cosmic timescales and human timescales overlap. Astronomers who first pointed their telescopes at it in 1996 are now handing the baton to a new generation of researchers who will carry on the watch. The story of Sakurai's object has become a multi-generational project, uniting scientists across time, nations, and instruments in pursuit of understanding. A lesson in patience and persistence. Sakurai's object reminds us that astronomy is not always about the spectacular discovery or the instant breakthrough. Sometimes, it is about patience, about keeping a steady watch over decades, knowing that the universe reveals its secrets slowly. And yet, in this case, it is also about urgency. Every year brings new changes, and missing even a small piece of the puzzle could mean losing an insight that won't come again for millennia. So the vigil continues, and Sakurai's object remains one of the most carefully observed stars in the galaxy. When astronomers talk about stars, one of the most fundamental tools they use is the light curve, a simple graph that shows how a star's brightness changes over time. For most stars, the light curve is steady, predictable, and unremarkable. For variable stars, the pattern may be rhythmic, pulsing with regularity like a beating heart. But for Sakurai's object, the light curve has been anything but ordinary. Instead, it has been chaotic, irregular, and puzzling, reflecting the turbulent and unpredictable nature of a star caught in the act of being reborn. The first brightening in 1996. When Yukio Sakurai first spotted the object in February 1996, what he saw was the first major spike in brightness. To telescopes and even to the naked eye under good conditions, it looked like a new star had suddenly appeared. The initial light curve showed a dramatic rise, brightening several magnitudes in just a matter of weeks. Normally, such a rise might suggest a nova, a white dwarf flaring up after accreting matter from a companion. But the absence of other telltale nova features made astronomers quickly realize this was something stranger. That first spike set the stage, but it was only the beginning of a roller coaster light curve that would continue for years. Sudden dimmings, the dust effect. After its initial rise, Sakurai's object didn't settle into steady brightness. Instead, it began to fade, sometimes dramatically. At first, this dimming puzzled astronomers. Was the star itself losing energy? Was nuclear burning shutting down again? But closer inspection revealed the culprit: dust. As the star's atmosphere expanded and cooled, it began to condense carbon-rich dust. This dust formed thick clouds that obscured the star's light from view, much like storm clouds blotting out the sun. Each new wave of dust formation produced sharp declines in visible brightness, sometimes almost completely erasing the star from optical telescopes. This made the light curve jagged, full of sudden plunges and recoveries. It wasn't the star fading and brightening internally. It was the dust veil thickening and thinning, changing how much starlight could escape. Brightening in the infrared. Here's where things got fascinating. While the star's visible light dropped dramatically due to dust, its infrared emission rose. Dust doesn't just block light, it absorbs it and re-emits it at longer, cooler wavelengths. So when Sakurai's object dimmed in optical light, infrared telescopes actually saw it getting brighter. This created a kind of dual light curve, one in the optical showing erratic fades, and one in the infrared showing surges. Together, they revealed the full story of how dust was forming, thickening, and redistributing the star's energy output. Unpredictable behavior. The variability of Sakurai's object has been maddening for astronomers trying to model it. Unlike many variable stars, there is no simple rhythm or cycle to its behavior. Instead, its brightness changes seem tied to chaotic processes. A dust formation in irregular bursts. A shifts in the star's atmosphere, as helium burning pulses altered its internal structure. A collisions of outflowing gas with the surrounding nebula, which may have sparked sudden brightenings. This makes the light curve a kind of cosmic heartbeat, but one with arrhythmias and erratic jumps, more like the flatline and spike patterns of a patient in crisis. Lessons from the variability. While confusing, the erratic light curve has been a goldmine of data. Each dimming and brightening has taught astronomers something new. A dust chemistry. By analyzing the timing and wavelengths of brightness dips, researchers learned how carbon-rich dust forms and evolves around dying stars. A timescales of stellar change. The irregularity showed that dramatic shifts in stellar atmosphere can happen in months, not millennia. The nature of born-again stars. The unpredictability of the light curve became one of the hallmarks of the born-again phenomenon. What's more, the variability meant that astronomers had to stay constantly alert. Missing a few months of data could mean missing a sudden transformation. A star that refuses predictability. The strangest part is that, even now, decades later, Sakurai's object continues to show variability. It hasn't settled into a neat fade or a stable plateau. It remains erratic, as though it refuses to be predictable. In a sense, that's fitting. Sakurai's object is a star that defied death and broke the rules of stellar evolution. Why should its light curve behave any differently? A cosmic reminder. The unexpected variability of Sakurai's object is more than just an observational detail. It's a reminder that the universe does not always follow neat, clean patterns. For every textbook diagram of stellar evolution, there are real stars like this one that twist, shatter, and rewrite the rules. Watching its light curve has been like watching a cosmic ECG, where the universe itself shows us that even in the realm of stars, life and death are messy, unpredictable, and full of surprises. When Sakurai's object erupted into its brief, chaotic renaissance in 1996, astronomers didn't just see an astronomical curiosity, they saw a theoretical challenge. It was as if the universe had tossed a puzzle piece onto the table that didn't quite fit the picture astrophysicists thought they had assembled. Every dip and surge in brightness, every dust cloud, every shift in chemistry forced scientists to revisit, refine, and in some cases rewrite their models of stellar evolution. This is where Sakurai's object transformed from an oddity into a revolution in theory. It pushed the boundaries of what we thought possible for dying stars, and it helped bring clarity to a particularly mysterious concept in astrophysics, the late thermal pulse, or final helium flash. The pre-1996 models. Before Sakurai's object, astrophysicists had a general understanding of how stars like the Sun live and die. The sequence was clear enough. 1. Burn hydrogen for billions of years. 2. Expand into a red giant when hydrogen is gone. 3. Burn helium for a while, then shed the outer layers. 4. Leave behind a glowing white dwarf surrounded by a planetary nebula. 5. Cool into darkness over trillions of years. That was the textbook pathway. And while the idea of a late helium flash had been proposed, it was treated as an almost hypothetical event. Models suggested it might occur if the star's helium shell reignited after it had already become a white dwarf, but no one had watched such a thing happen in real time. The theory was there. The data wasn't. Enter Sakurai's object. Proof of concept. Sakurai's object changed everything. Here was a real star, only 20,000 light-years away, doing exactly what the models had predicted in outline but never in detail, reigniting, swelling back up, and reversing its apparent age. The sudden brightening matched the expected surge of energy from a helium shell flash. The dust formation matched predictions that such stars would shed carbon-rich material during this violent rebirth. The strange, hydrogen-poor atmosphere matched the models of a white dwarf dredging up deeper layers when reignition occurred. Suddenly, what had been a footnote in stellar theory became front-page news in astrophysics. Refining the late thermal pulse models. Of course, the story wasn't as simple as the models were right. If anything, Sakurai's object exposed just how much those models had left out. The speed, complexity, and chaos of the star's evolution were far more dramatic than most simulations had suggested. A timescale shock, Models had implied that changes from a helium flash would take thousands of years. Sakurai's object did it in months. This forced theorists to reconsider the physics of energy transport in stellar interiors. Dust dynamics. While models predicted dust, they hadn't anticipated how quickly it could obscure a star entirely. Astronomers had to fold in new insights about carbon chemistry, grain growth, and mass loss rates. Chemical signatures. Observations revealed unusually high abundances of carbon and heavier elements, challenging nucleosynthesis models and requiring recalibration of how convection dredges up stellar material. Light curve variability. No model had predicted the kind of jagged, irregular light curve Sakurai's object displayed. New simulations had to account for episodic mass loss and pulsations driven by unstable nuclear burning. In short, the event became a stress test for stellar theory, forcing astrophysicists to fix what was too simple, too smooth, or too slow in their equations. Computer models after Sakurai. The late 1990s and 2000s saw a flurry of computational work inspired directly by Sakurai's object. Supercomputers were tasked with simulating final helium flashes in far greater detail, with better treatment of convection, mixing, and nuclear burning rates. Some breakthroughs included improved handling of convective overshoot, explaining how deep stellar material was mixed to the surface. Models of episodic dust ejection, capturing how the star could brighten and dim unpredictably. Refined estimates of the frequency of born-again events, suggesting that while rare, they may be an expected outcome for a small fraction of Sun-like stars. Sakurai's object essentially became the lab rat of stellar evolution theory. Every tweak to the equations was tested against its observed history. If the model couldn't reproduce Sakurai's bizarre light curve and chemical shifts, it wasn't good enough. A broader impact, beyond one star. The implications went beyond just explaining this one star. Sakurai's object gave astrophysicists tools to interpret other mysterious objects in the galaxy and beyond. RFG Sagittarius and V605 Aquila, earlier born-again candidates, could now be reinterpreted with fresh models, confirming that they too fit the late thermal pulse framework. Planetary nebulae. Some planetary nebulae with hydrogen-poor central stars could now be understood as remnants of stars that had undergone a born-again phase. Stellar populations. Models of galactic chemical enrichment had to consider how born-again stars might contribute dust and heavy elements to the interstellar medium. What started as a curiosity became a cornerstone of how we understand the messy deaths of sun-like stars. The human side of theoretical progress. It's worth noting the emotional and intellectual impact on the scientific community. For theorists who had spent years refining equations about late helium flashes, Sakurai's object was like a dream come true, an actual experiment unfolding in the heavens, testing their predictions in real time. For others, it was a nightmare of complexity. The event revealed just how little we knew about the fine details of stellar interiors. It forced humility, reminding astronomers that nature always has more imagination than we do. Either way, the star energized the field, sparking new collaborations, debates, and papers that continue to this day. The legacy for stellar models. Today, any serious discussion of stellar evolution includes Sakurai's object as a case study. It's no longer just a curiosity, it's a benchmark. Models of sun-like stars now routinely include the possibility of late thermal pulses. Simulations of white dwarfs acknowledge that they may not always fade quietly into darkness. And thanks to Sakurai's object, we know that the universe occasionally rewinds the clock, giving us a glimpse of a process once thought invisible. A universe of surprises. At its core, the lesson of Sakurai's object for theoretical models is simple: expect the unexpected. Stars may follow broad evolutionary tracks, but the fine print is full of surprises. Sakurai's object reminded us that the cosmos isn't just orderly and predictable, it's wild, dynamic, and sometimes rebellious. The story of Sakurai's object is not just about stellar physics, it's also about timing. Timing so improbable, so delicate, that one could almost call it miraculous. For all our advancements in astronomy, from orbiting observatories like Hubble to ground-based telescopes armed with adaptive optics, one truth remains: we cannot predict exactly when a star will flare into a born-again phase. And that makes Sakurai's object one of the greatest strokes of luck in modern astronomy. Why is timing so hard to predict? To understand why prediction is impossible, we have to remember what triggers the born-again event, the final helium shell flash. This flash comes from a thin shell of helium buried deep inside the star, hidden under layers of carbon, oxygen, and residual hydrogen. The instability that causes it is subtle, chaotic, and highly sensitive to tiny details in the star's internal structure. Astronomers can model the general likelihood that some white dwarfs may undergo a flash. But knowing when it will happen? That's like trying to predict the exact second a dormant volcano will erupt. The physics is chaotic. A slight variation in mass, composition, or previous evolutionary history can alter the timing by thousands, or even millions, of years. So when astronomers observed Sakurai's object flare in February 1996, it wasn't the result of a prediction. It wasn't that anyone had been watching that particular point in the sky expecting drama. It was pure coincidence. Why this makes the event so rare for humans? Think about this. Stars live for billions of years. A born-again phase, if it happens at all, may last only a few decades at most. That means the window to witness one is unbelievably small compared to the vast cosmic timeline. Imagine standing on a beach with grains of sand representing stellar lifetimes. Each grain is billions of years long. A born-again event? That would be a scratch on the surface of one grain. The odds of humans, in their tiny flicker of existence, catching one of these scratches in progress is almost zero. And yet, we did. This is what makes Sakurai's object so extraordinary. Not just the science, but the sheer improbability of our timing. Out of all the stars in the galaxy, out of all the eras humanity could have existed, we happen to be here, with telescopes in hand, at the exact moment one of the rarest stellar acts unfolded. A cosmic lottery ticket. In many ways, Sakurai's object is like winning a galactic lottery. Astronomers often compare rare cosmic events to rolling dice or winning lotteries, but this one truly fits the metaphor. Not only did a rare born-again event happen, it happened close enough. 20,000 light-years is near in cosmic terms, and in a direction we could easily observe from Earth. And it happened in the late 20th century, when our technology was advanced enough to capture it in detail. Had this star flared in, say, the 1500s, we would have had no way to understand it. Had it occurred 50,000 light-years away in the far side of the galaxy, we might never have noticed. And had it erupted even a few decades earlier, before Hubble or modern infrared telescopes, we would have missed many of its most important features. The timing wasn't just rare, it was perfect. The frustration of unpredictability. Of course, the flip side of this cosmic luck is frustration. Astronomers now know what to look for in a born-again event. They know the chemical signatures, the light curve patterns, the dust production. But they cannot forecast when the next one will happen. There's no warning system. No precursors detectable from Earth that say, this white dwarf is about to ignite. This makes Sakurai's object all the more precious. Every scrap of data, every archival image, every spectrum is irreplaceable. Because we cannot know if another born-again star will reveal itself in our lifetimes, or if this was the only one humanity will see for centuries. Philosophical implications. The timing also speaks to something deeper. It reminds us how fragile and fleeting human observation is. We are creatures of decades, yet we chase the secrets of stars that live for billions of years. Most stellar processes are so slow that they escape our notice entirely. And yet, for reasons we may never fully understand, the cosmos sometimes gives us a glimpse of something astonishing right on our watch. The born-again star is like a whispered secret, entrusted to us by chance. It makes Sakurai's object not just a scientific event, but a poetic one. It suggests that even in a universe governed by physics and probability, there are moments that feel almost designed for wonder. Lessons for future astronomy. The unpredictability of timing has also shaped how astronomers prepare for the future. Since Sakurai's object, there has been a growing emphasis on all-sky surveys, telescopes that monitor vast swaths of the sky continuously. The idea is simple. If you can't predict when a rare event will happen, you can at least increase your chances of catching it by watching everything, all the time. Projects like the Vera C. Rubin Observatory, expected to begin its legacy survey of space and time, are, in part, responses to the lesson of Sakurai's object. They acknowledge that the cosmos won't announce when the next rare event is coming. We must be ready to capture it at any moment. The wonder of chance. In the end, the mystery of timing is both a limitation and a gift. We cannot know when the next born-again star will ignite. We cannot control the cosmic dice. But the very fact that Sakurai's object appeared in 1996, dazzling our instruments and our imaginations, is a reminder that the universe occasionally throws us a surprise. It was luck, yes. But it was luck wrapped in meaning. A once-in-many-lifetimes event that told us, in no uncertain terms, that the cosmos is alive with possibilities far stranger and rarer than we usually dare to imagine. The impact of Sakurai's object on astronomy cannot be overstated. For centuries, humanity has studied the heavens, trying to piece together the life stories of stars. We had theories, simulations, and models that attempted to describe how stars are born, evolve, and eventually die. But when it came to rare transitional phases, fleeting, unstable episodes that happen in the blink of a cosmic eye, we were largely working with fragments. Then, in 1996, Sakurai's object handed astronomers something unprecedented, a direct, living example of a star reborn. It was not just another star in the night sky. It was a living laboratory, a cosmic experiment running in real time, allowing us to watch what had previously been inferred only from ancient remnants or mathematical equations. Shattering textbook simplicity. Before Sakurai's object, stellar evolution was often taught in neat, orderly steps. Main sequence, red giant, planetary nebula, white dwarf. End of story. There were hints of exceptions, FG Sagittarius, V605 Aquila, but they were distant, ambiguous, and not well monitored with modern technology. Sakurai's object smashed that simplicity. It was proof that stellar death is not always final. The born-again phenomenon became more than just a theoretical curiosity. It became an observed reality. Textbooks had to be revised, lectures rewritten, and models retooled to account for this astonishing twist in the lives of some stars. This shifted astronomy from asking, "Is the born-again phase real?" to "How often does it happen, what exactly triggers it, and what does it mean for stellar populations in our galaxy?" A real-time stellar evolution case study. Most of the time, astronomers reconstruct stellar evolution the way archaeologists reconstruct ancient civilizations, from ruins, remnants, and indirect evidence. Planetary nebulae, white dwarfs, and supernova remnants tell us what once happened. But Sakurai's object gave astronomers something far rarer, the chance to watch the process unfold in real time. The sudden brightening, the dust obscuration, the atmospheric transformations, these were not static fossils frozen in space, but dynamic, ongoing processes. It was like watching a time-lapse of stellar evolution compressed into decades rather than eons. Astronomers could point their instruments at the same star year after year and document dramatic changes, a phenomenon virtually unheard of in the field of stellar astrophysics. Confirmation of late thermal pulses. Another major impact was confirmation. The idea of late helium shell flashes had been proposed decades earlier, but without direct observation, it remained speculative. Sakurai's object confirmed the existence of final helium flashes, validating decades of theoretical work. This gave astrophysicists more confidence in their models of stellar interiors. It also provided real observational data, chemical abundances, dust formation rates, light curves, that could be plugged back into simulations. The result was a dramatic improvement in our understanding of what happens inside stars as they approach the very end of their lives. The importance of dust and chemistry. Sakurai's object also highlighted the central role of dust in stellar and galactic evolution. The carbon-rich dust it spewed into space was not just an observational inconvenience, it was a crucial part of the cosmic recycling process. Stars like Sakurai's object manufacture heavy elements in their cores, then release them into space through outflows and eruptions. This material enriches the interstellar medium, providing the raw ingredients for future stars and planets. By observing how Sakurai's object formed and distributed dust, astronomers gained insight into how galaxies themselves evolve chemically over billions of years. It showed, in other words, that born-again stars are not just curiosities, they are contributors to the great cosmic cycle of matter. Technological and observational shifts. The star also forced astronomers to rethink their observational strategies. Its rapid variability meant that old habits, checking on an object once every few years, were insufficient. Sakurai's object demanded continuous, multi-wavelength monitoring. This lesson rippled across the field. The rise of time-domain astronomy, the study of how celestial objects change over time, was partly fueled by events like this one. It underscored the need for automated sky surveys, constant monitoring, and flexible telescopes that could react quickly to sudden stellar outbursts. The event also emphasized the importance of infrared astronomy. When dust obscured the star in visible light, only infrared instruments could continue tracking it. This justified further investment in infrared observatories, both on the ground and in space. Inspiration for astronomers and the public. Sakurai's object also had a profound cultural impact. For professional astronomers, it was exhilarating, proof that the universe still holds surprises, that even a well-studied field like stellar evolution could present phenomena no one had truly witnessed before. For the public, the story of a dead star coming back to life carried an almost mythic quality. It captured imaginations, reminding us that stars are not just static points of light, but dynamic, evolving entities with stories as dramatic as any legend. A new kind of astronomical object. Perhaps the most lasting impact was simply this: before 1996, born-again stars were a theoretical footnote. After 1996, they became an observational reality, a recognized class of objects. Sakurai's object became the archetype, the touchstone against which other possible born-again stars were compared. Its dataset became a benchmark, a reference point, a guiding case study for stellar astrophysics. The broader lesson. In summary, the impact of Sakurai's object on astronomy was both specific and sweeping. Specifically, it confirmed the existence of final helium flashes, advanced our understanding of dust and stellar atmospheres, and provided a rare laboratory for observing stellar change in real time. But more broadly, it reminded us of something fundamental: that the universe is not a finished puzzle, neatly solved, but a living mystery that still holds surprises. It taught us humility, awe, and vigilance, that even in the familiar night sky, there are stars waiting to upend everything we thought we knew. When we shift our gaze from the details of Sakurai's object to the cosmic perspective, the story takes on an even deeper resonance. Human beings live fleeting lives, measured in decades. Civilizations rise and fall in the span of a few thousand years. Even our entire recorded history is a mere heartbeat compared to the lifespan of stars. And yet, against all odds, we happen to be alive at just the right moment, in just the right corner of the universe, to witness something so rare that it defies probability: a dead star suddenly coming back to life. Human timescales versus stellar timescales. To appreciate the enormity of this, let's consider the timescales involved. A star like our Sun lives for about 10 billion years. For the first 90% of that time, it quietly fuses hydrogen into helium on the main sequence, shining steadily with little visible drama. Then, over hundreds of millions of years, it swells into a red giant, sheds its outer layers, and finally becomes a white dwarf. Most of these changes occur so slowly that no single human generation could possibly notice them. To us, stars appear unchanging, eternal points of light. Our lives are too short to perceive the gradual evolution written into their nuclear cores. And yet, Sakurai's object defied that expectation. It evolved so rapidly that the changes could be observed not just across centuries, but across months and years. For the first time, humanity was able to see with its own eyes a process that normally unfolds invisibly across eons. It's as if the universe momentarily bent its timescale to meet ours, compressing thousands of years of stellar evolution into the span of a single human career. The rarity of our witnessing. This cosmic coincidence raises an almost philosophical question. What are the odds that we would be here, at this exact moment, to watch a born-again star? Out of hundreds of billions of stars in our galaxy, only a handful are ever expected to undergo a final helium flash. And even among those few, the window during which the process is visible, when the star brightens, forms dust, and reshapes its atmosphere, is vanishingly short. We were lucky. Lucky to have astronomers watching the sky. Lucky that an amateur like Yukio Sakurai happened to look in the right place at the right time. Lucky that technology had advanced enough to capture the event across multiple wavelengths. This is one of those moments that makes us realize how precious astronomical observation really is. The universe doesn't schedule its wonders for our convenience. If we blink, or if our civilizations stop looking, we may miss the greatest spectacles the cosmos has to offer. A mirror for humanity. In its cosmic context, Sakurai's object becomes more than an astrophysical curiosity. It becomes a mirror, reflecting the fragility of our own perspective. Stars live for billions of years. We live for dozens. To a star, our entire species is a brief flicker, a passing moment. Yet in our short time, we have developed the ability to see across 20,000 light-years, decipher stellar chemistry, and witness rebirth on a cosmic scale. This juxtaposition is humbling. We are so small, so brief, and yet capable of such immense perception. The sense of cosmic theater. There's also a poetic element here, the idea that the universe stages events that we sometimes, against all odds, manage to witness. A star dies, fades into obscurity, and then, unexpectedly, flashes back to life, almost as if to remind us that death in the cosmos is rarely final. To think that this occurred in Sagittarius, a constellation long associated with mythology, archery, and cosmic symbolism, adds yet another layer of resonance. Thousands of years ago, ancient civilizations looked to this same region of the sky with stories and imagination. And in 1996, humanity added a new story, the star that returned from the dead. Cosmic perspective as a lesson. The broader lesson of Sakurai's object is that our perspective is painfully limited. We are creatures of fleeting moments, but the cosmos stretches across gulfs of time so vast that even our imaginations struggle to grasp them. And yet, sometimes, by chance, we align with something extraordinary. For a handful of decades, we are alive at the exact right time to watch a star resurrect itself. For a fraction of cosmic history, we get to bear witness to processes that remind us of our place in the universe. Tiny, fleeting, but not insignificant. Because in seeing this star's rebirth, we glimpse not only the mechanics of stellar evolution but also the grandeur of cosmic time, a reminder that existence is both fragile and enduring, both ephemeral and infinite. The human thread in a cosmic story. This is why Sakurai's object matters beyond the science. It connects our brief human stories to the much longer, much older story of the stars. The photons that reached our telescopes in 1996 had been traveling for 20,000 years, leaving the star's surface back when human civilization was barely taking its first steps. By the time they arrived, we were here, ready to understand them. In that sense, Sakurai's object is both a stellar event and a human one. It bridges the incomprehensible scale of cosmic history with the fragile brevity of human time, reminding us that, for all our limits, we are capable of catching stars in the act of transformation. As we step into the present day, the story of Sakurai's object is far from over. In fact, what makes this star even more fascinating is that its evolution has continued before our eyes for decades. Unlike most astronomical events, which either last millions of years or flash by in seconds, Sakurai's object has unfolded in a humanly accessible time frame, long enough for us to monitor consistently, yet fast enough that we see real change within a single career span. This places it in a unique category, a living laboratory of stellar rebirth. Still hidden in dust. Today, Sakurai's object is almost completely invisible in visible light. The carbon-rich dust that began forming in the late 1990s has only grown thicker and more extensive, enshrouding the star in a dense cocoon. To optical telescopes, the once bright star has all but disappeared. This is not surprising. Born-again stars are known to generate prodigious amounts of dust. The violent helium flash and the rapid swelling of the star's outer layers created the perfect conditions for dust grains to condense. In Sakurai's case, the dust became so dense that it essentially built a dark shroud around the star, blocking almost all visible photons from escaping. But as often happens in astronomy, when one window closes, another opens. The infrared window. Although the dust blocks visible light, it re-emits absorbed energy as infrared radiation. This means that while the star vanished from optical observation, it became a beacon in the infrared. Astronomers using instruments like the Infrared Space Observatory, ISO, Spitzer Space Telescope, Herschel Space Observatory, and various ground-based IR telescopes have been able to trace its evolution long after it disappeared from optical view. Through infrared monitoring, scientists have watched the dust shell expand outward, cool, and evolve. They've seen temperature changes, chemistry shifts, and even irregular density structures suggesting the dust was not expelled evenly but in complex patterns. possibly influenced by magnetic fields or asymmetric ejection. In a sense, Sakurai's object has become a cosmic ember, glowing through its veil, offering astronomers an ongoing view into the mechanics of dust and post-flash evolution. Shrinking back toward a white dwarf. One of the most intriguing developments in the current status of Sakurai's object is that it appears to be recontracting. After the helium flash, the star swelled dramatically, mimicking a red giant once again. But recent observations suggest it is now beginning to shrink, heating back up, and moving once more toward the white dwarf phase. This is exactly what theoretical models predicted for a born-again star, a violent, temporary return to a giant-like state, followed by a rapid fallback into its final, cooling embers. For Sakurai's object, this transition has taken only a few decades, a blink of an eye compared to normal stellar evolution. We are witnessing, in real time, the reverse journey from red giant back to white dwarf. Planetary nebula interactions. Another important part of its present story lies in the interaction between the star's new ejector and the old planetary nebula left over from its first death. When Sakurai's object underwent its original red giant phase thousands of years ago, it expelled its outer layers into space, creating a faint planetary nebula. Now, the fresh material ejected during its rebirth, dust, gas, and winds, is colliding with that older nebula. Astronomers using the Hubble Space Telescope have observed knots, shocks, and structural changes in the surrounding gas as the new ejector slam into the relic shell of the past. This creates a rare double-layered environment, an old death shroud interacting with a new burst of life. It's as though the star's history and present are colliding in a visible fireworks display, written across light-years of gas and dust. Hydrogen-poor atmosphere. Spectroscopic studies continue to confirm that Sakurai's object has a hydrogen-poor, carbon-rich atmosphere. This remains one of the most important signatures of its final helium flash. In its reborn phase, the star dredged up deeper layers of its core material, exposing fusion products like carbon and helium at the surface while almost entirely depleting hydrogen. This chemical fingerprint is not just a curiosity. It helps confirm the born-again model and allows astronomers to connect Sakurai's object to other suspected late thermal pulse stars across the galaxy. The star today, a ghost wrapped in dust. So, what is Sakurai's object like right now? Optically invisible. You can't see it with ordinary telescopes. Infrared bright. It still glows strongly in the IR as dust radiates absorbed heat. Recontracting. Evidence suggests it is slowly returning to a compact, hotter state. Still evolving rapidly. Changes continue on yearly timescales, keeping astronomers engaged. In essence, it has become a kind of astronomical ghost, shrouded, hidden, yet still whispering clues about its fate through the faint glow of its dust. Why its current state matters. What makes the present-day status of Sakurai's object so compelling is that it's not just a static remnant. It's still changing in real time. Astronomers continue to measure new shifts in its brightness, dust density, and infrared emissions. Each year adds another chapter to its story, and no one knows exactly how long the reborn phase will last. Some models suggest it may soon stabilize as a white dwarf again, entering the slow fade it should have experienced originally. Others wonder whether its dust and ejected gas may continue producing unpredictable events, prolonging its visibility in infrared. Either way, Sakurai's object remains one of the few stars that we can watch die twice. The ongoing vigil. Even now, more than 25 years after its discovery, astronomers continue to monitor Sakurai's object with instruments ranging from ground-based IR detectors to the James Webb Space Telescope, JWST. JWST, with its unparalleled infrared sensitivity, is especially well suited to pierce the dust veil and reveal details of the star's inner workings. Early results hint at even more surprises waiting in the obscured core. For the scientific community, Sakurai's object has become a long-term project, a reminder that some discoveries are not quick bursts of data but decades-long commitments, evolving alongside our technology. Even after nearly 3 decades of observation, Sakurai's object remains one of the most mysterious stars ever studied. For all the progress made in understanding its unusual rebirth, there are still more questions than answers. In fact, one could argue that its greatest gift to astronomy has not been the data we've collected but the questions it forces us to ask. Questions that probe the very limits of our models of stellar evolution. Questions that remind us how little we truly know about the delicate balance between life and death in stars. How long will the born-again phase last? Perhaps the most pressing question is, how long can Sakurai's second life continue? When the star experienced its final helium shell flash in the 1990s, it was essentially yanked backward along its evolutionary path, swelling outward like a red giant once again. But this reborn state is, by nature, unstable. Born-again stars are not destined to remain giants forever. They eventually lose the energy that drives this temporary renaissance. Some models suggest that the born-again phase might last only decades. If that's the case, Sakurai's object may already be well along the road back to its white dwarf form, its brief rebirth just a cosmic flicker. Other models argue it could persist for centuries, with the star continuing to throw off dust, interact with its nebula, and remain hidden in infrared light long after our generation has passed. Right now, no one knows which prediction is correct. What we do know is that the evolution is happening much faster than most theories initially expected. That means its end, whatever form that takes, could come sooner rather than later. Will it shrink back into a white dwarf? A second major question is whether Sakurai's object will ultimately return to being a white dwarf. The general consensus is yes. Once the helium flash subsides and the star can no longer sustain its expanded outer layers, it should contract once more into a small, dense core, resuming the long, slow cooling process it was already on before its rebirth. But the path back may not be smooth. Some models predict additional instability along the way, further dust eruptions, unpredictable brightening and dimming events, even potential miniflashes as residual shell material reacts to changes in pressure and temperature. In other words, Sakurai's object might not go quietly. It could stumble, flare, and flicker before finally settling back into its true role as a cooling stellar corpse. Will it die again in the same way? Another provocative question: can a born-again star be born again? So far, evidence suggests that Sakurai's object is unlikely to experience another full-scale helium flash once it recontracts. The conditions that triggered its late thermal pulse were rare and delicate, essentially a one-time cosmic accident. However, astronomers can't entirely rule out smaller convulsions or eruptions as it continues to stabilize. If Sakurai were to show evidence of repeated flashes, it would force a revolution in stellar theory, as this would mean stars might not just die twice, but possibly 3 times or more, each rebirth leaving a new imprint on the surrounding nebula. Why did it happen now? Timing remains one of the greatest mysteries. Why did this star's helium shell ignite exactly when it did, just as humanity had telescopes capable of monitoring it? The late helium shell flash is incredibly rare, and there was no way to predict it in advance. That we caught Sakurai's object in the act may have been pure luck, a cosmic coincidence. But some wonder if it hints at subtler patterns in stellar interiors. Maybe certain types of stars are more prone to born-again events, and we just don't yet know how to identify them beforehand. If astronomers can figure out what sets Sakurai's object apart, its initial mass, metallicity, or internal structure, it could unlock a predictive framework for spotting future candidates before they erupt. How unique is Sakurai's object? Related to timing is the broader question of rarity. Are born-again stars genuinely as rare as we think, or do we simply fail to recognize them? It's possible that many stars across the galaxy experience brief helium flashes, but unless they are close enough or bright enough, we don't notice them. The veil of dust they generate can hide them from optical surveys, and unless astronomers are actively monitoring in the infrared, such events could slip past unnoticed. This raises an intriguing possibility. The universe may be scattered with hidden Sakurai-like events, and we're only just learning how to look for them. What will happen to its nebula? Another unanswered question lies outside the star itself. What will become of the planetary nebula surrounding Sakurai's object? As the newly ejected dust and gas from its rebirth collide with the older shell of material, they create turbulence, shocks, and chemical mixing. Over centuries, this could dramatically reshape the nebula. But will the new material enrich the nebula with unusual compositions, creating a chemical fingerprint of its 2 deaths? Or will the dust eventually dissipate, leaving only the ghost of its original ejection thousands of years ago? The answer could give astronomers vital clues about how born-again stars leave lasting imprints on their galactic environments. What role do born-again stars play in cosmic chemistry? A more subtle, But no less important question: how much do stars like Sakurai's object contribute to the galaxy's overall chemical evolution? During their born-again phase, these stars eject huge amounts of carbon-rich dust. This dust eventually mixes with interstellar gas, becoming part of the raw material for new stars and planets. In this sense, born-again stars may act as cosmic spice, seasoning the galaxy with rare elements in ways we have yet to quantify. If born-again stars are more common than we think, they could play a bigger role in galactic ecology than we've ever realized. Can we predict the future of our own sun? Perhaps the most profound open question is personal. Could our sun undergo a similar rebirth? We know the sun will one day swell into a red giant, shed its outer layers, and shrink into a white dwarf. But could it, millions of years later, briefly come back to life with a final helium flash? Current models suggest it's possible, though not guaranteed. The uncertainty lies in the fine details of stellar structure and composition, details we are only beginning to probe thanks to objects like Sakurai's. If Sakurai's object teaches us anything, it's that stellar deaths are more complicated, more dynamic, and more surprising than the neat diagrams in textbooks suggest. A star that won't stop asking questions. Ultimately, Sakurai's object has become less a solved case and more a cosmic riddle. Each year of observation adds data, but also raises new puzzles. How long will its second life last? Will it stabilize peacefully, or continue erupting unpredictably? How much dust will it contribute to its nebula and the wider galaxy? Can its behavior be modeled well enough to predict future born-again stars, or even the future of our sun? For now, these questions remain open, hanging in the space between theory and mystery. And that is perhaps the most beautiful part of Sakurai's object. It refuses to be neatly categorized. It resists closure. It continues to live in uncertainty, just as we continue to watch it with awe. As we arrive at the closing reflection of this long journey into the mystery of Sakurai's object, it is impossible not to feel a sense of awe. This is more than just a tale of astrophysics, equations, and telescopes. It is, at its heart, a story of life and death, of endings that are not truly endings, and of how even in the vast, cold universe there can be moments of second chances. Think of what we have witnessed. A star that should have been silent, a stellar corpse cooling in the shadows, suddenly flaring back into brilliance. It was a moment that defied not only human expectations but also the very laws we thought governed stellar life. And yet, it happened, an undeniable truth, written across the sky for anyone with eyes to see. This phenomenon is scientific, yes, but it is also deeply poetic. For when we say Sakurai's object was born again, we are not only describing nuclear fusion and helium shell flashes. We are describing resurrection. We are describing the impossible act of a star refusing to stay dead, roaring back into vitality even after its supposed final breath. It is as if the universe itself wanted to remind us that endings are never as simple as we think. There is something profoundly human in this. We, too, live with the awareness of time, of decay, of inevitable death. But Sakurai's object teaches us that even within the strictest rules of nature, there are exceptions. There are rebellions. There are stars that take one last breath and shine again, even if only for a short time. And in that shining, they give us knowledge, beauty, and wonder. When astronomers point their telescopes towards Sakurai's object, they are not just measuring light curves or analyzing dust composition. They are watching a cosmic metaphor unfold before their eyes, that nothing is ever truly lost, that even in death there can be transformation. The white dwarf that should have been silent became a teacher, offering humanity a rare, fleeting classroom in the very heart of Sagittarius. And so, perhaps the greatest lesson of Sakurai's object is not just about stellar evolution. Perhaps it is about perspective. We, the inhabitants of one small world orbiting a middle-aged star, often think of our time as fleeting, fragile, and unimportant. And in the cosmic sense, it is. Stars live for billions of years, galaxies for trillions. Our lives, our civilizations, our histories, these are but sparks compared to the immensity of the cosmos. But then, there is Sakurai's object. It tells us that sometimes, the universe bends low enough for us to witness miracles. That sometimes, out of the unthinkable expanse of time and distance, we are granted the privilege to witness a story so rare, so fleeting, that it feels as though it was meant for us alone. The star's second chance coincided with humanity's golden age of telescopes, as if the cosmos knew we were finally ready to understand. And here we stand, observers of a star's rebirth, keepers of its story, and students of its lessons. The next time you look up at the night sky, remember Sakurai's object. Remember that even stars, those colossal engines of creation, can falter, can die, and can rise again. Remember that the universe is not a machine of only cold logic, but a stage for drama, mystery, and poetry. Remember that sometimes, against all odds, there are second chances. Stars may die, but Sakurai's object reminds us, the end is not always the end. Sometimes, even in the silence of eternity, there is a whisper of rebirth. Sometimes, even in the vast loneliness of space, there is a spark of hope. And perhaps, in that truth, we can see a reflection of our own lives. That we, too, may stumble, may fall, may fade, but there is always the possibility of light returning. Always the possibility of a second chance. That is the legacy of Sakurai's object. Not just a scientific curiosity, but a cosmic parable, that death is not always final, that time is not always linear, and that even the stars themselves may find their way back to life. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.